So, here's something to sit with as you settle in tonight. On April 10th, 2019, 6 simultaneous press conferences were held around the world. Washington, Brussels, Santiago, Shanghai, Taipei, Tokyo. And at each one, at the exact same moment, they showed the same image. A blurry ring of orange and gold light, bright on one side, dimmer on the other, surrounding a dark center. That was it, a slightly fuzzy circle, and grown adults, scientists who had spent their entire careers waiting for this moment, some of them cried. Because that fuzzy circle was the first photograph of a black hole. Not an illustration, not a simulation, not an artist's impression from a textbook. A real image, assembled from real photons, photons that had crossed 55 million light-years of intergalactic space before landing on radio dishes scattered across 6 continents and the South Pole.
And those photons had come from the edge of an object 6.5 billion times more massive than our Sun. An object whose gravitational pull is so severe that any light falling past a certain boundary can never come back out. The image showed what that boundary looks like from the outside. A shadow, ringed by the superheated gas screaming around it at nearly the speed of light. And here's the thing that stayed with me long after the press conferences ended. What that photograph actually showed was absence. The bright ring, the glowing gas, that was the visible part, the part we could capture and process and color in orange for the newspapers. But the dark center, the black circle at the heart of it all, that was the story. That darkness wasn't empty space. It was a region of the universe where space-time itself has curved so severely that nothing, no signal, no particle, no beam of light can find a path back to us.
The darkness in that image is a place from which no information can return. We photographed a hole in the visible universe. Now think about that for a second. We are a species that understands the world by looking at things. Everything we know, everything science has ever figured out, starts with observation. Light hits our instruments and we build a picture. But black holes are the one place where that method breaks down completely. The thing that makes them remarkable, the very property that defines them, is that they don't let us see them. They hide. By their nature, by the deepest laws of physics, their interiors are sealed off from the rest of the universe forever. And yet we know they're there. We know how much they weigh. We know how fast they spin. We can describe the geometry of the space around them with equations so precise that the predictions match the observations to within a few percent. We have tracked individual stars whipping around an invisible center at thousands of miles per second, traced their full orbits over decades, and used those orbits to weigh something we have never seen and can never see. We have built detectors so sensitive that they can feel a passing ripple in the fabric of space-time. A ripple caused by 2 black holes colliding over 1 billion light-years away. A ripple that stretches and squeezes the distance between 2 mirrors by less than 1,000th the width of a proton. We felt that. We measured it. We extracted from it the masses and the spins and the final moments of objects that are, by definition, invisible. So here is the question that I keep coming back to, and it's the question I want to spend tonight with. How did we get here? How did a species that relies on seeing things come to understand the one thing in the universe that cannot, by its very nature, be seen? What exactly have we figured out, and what is still hiding in that darkness? Because the story of black holes is really a story about the boundary between what's visible and what's hidden. Every chapter of it follows the same strange pattern. Someone sees something, a mathematical result, a signal, an anomaly in the data. And that visible clue points towards something hidden, something that most people, often including the discoverer themselves, don't want to believe is there. Every breakthrough in this story happened because someone was willing to follow a visible clue into invisible territory. And every setback happened because someone looked at the visible clue and decided the hidden truth behind it was too strange, too unsettling, too fundamentally weird to be real. That pattern has been repeating for 240 years, and it hasn't stopped. Right now, tonight, there are questions about what's hidden inside black holes that represent the deepest unsolved problems in all of physics. Questions about whether information can truly be destroyed, or whether the universe has some deeper bookkeeping mechanism that preserves every bit of data, even when it falls past a point of no return. Questions about whether space-time itself is fundamental, or whether it emerges from something deeper, the way temperature emerges from the motion of trillions of atoms, something you can describe from the outside, but that doesn't exist at the most fundamental level. Questions about whether the entire three-dimensional universe you and I experience might be a kind of projection from a two-dimensional surface, a hologram woven from quantum entanglement. These aren't fringe ideas. These aren't science fiction. They're the cutting edge. And they all trace back to that same dark circle in the photograph. That shadow. That absence. That hole in the visible world. So tonight, I want to ask 3 questions. And I want to spend the rest of our time together working through them. First, the same force that's pressing you into your mattress right now, that quiet, familiar pull you've never spent a single second without. That force, under the right conditions, can crush a star the size of our sun down to something smaller than a city and trap light itself. How did we figure that out? How did we follow that gentle pull all the way to its most extreme and terrifying conclusion? And what did we find, waiting there? Second, right now, gravitational waves from colliding black holes are passing through your room, through your body, stretching and squeezing the space you're lying in by amounts too small to feel. We built machines that can feel them. We photographed the shadow of an object 55 million light-years away that, by its very nature, emits no light. So what do we actually know at this point, and what's still hidden from us, even after all of that? And third, black holes might be the most extreme objects in the universe, but the questions they've forced us to ask, about information, about the fabric of space, about whether the three-dimensional world you're lying in right now is actually fundamental or just a projection of something deeper, those questions reach far beyond black holes. They're questions about the nature of everything. So what does the darkness teach us? What does the thing we can't see tell us about the reality we can? So let's walk through it. The whole story, from the very beginning. Not quickly, not skipping the parts where people got it wrong or gave up or got in each other's way. Because the wrong turns matter as much as the breakthroughs.
The moments when brilliant people refused to believe what the mathematics was telling them are as important to this story as the moments when they finally accepted it. The resistance is part of the discovery. The hiding is part of the finding. Let's take it slowly. Let's start in 1783 with a quiet English clergyman who had a very simple idea and a very good question. And let's see where the visible clues lead us into the dark. To understand where this story begins, you have to understand something about gravity first. And I don't mean the equations, not yet. I mean the feeling. Because gravity is the most intimate force in your life. You have never been without it. From the moment you were born, it has been pressing on you, shaping you, pulling the blood down through your veins, keeping your feet on the ground, curving the arc of every ball you've ever thrown. It is so constant,
so pervasive, so much a part of every second of your existence that you probably haven't thought about it once today. It's like the hum of a refrigerator. You stop noticing it's there. But gravity is also the most democratic force in nature. It plays no favorites. Everything that has mass pulls on everything else that has mass. No exceptions, no opt-outs, no special immunity. The coffee mug on your bedside table is pulling on you right now. The pillow under your head is pulling on the moon. You are pulling on a galaxy 100 million light years away, and it is pulling back. The sun is pulling on a star halfway across the galaxy, and that star is pulling back. The force is incredibly weak between small objects, absurdly weak. The gravitational pull between you and the person next to you is trillions of times weaker than the force holding the atoms in your fingernails together. But gravity has a trick that no other force has. It always adds up. It never cancels. Electromagnetism has positive and negative charges that can neutralize each other. The nuclear forces operate only at subatomic distances, but gravity just keeps accumulating. The more mass you pile together, the stronger it gets, and it reaches across any distance. That's why gravity runs the universe. On the scale of atoms and molecules, gravity is a nobody. On the scale of planets and stars and galaxies, gravity is the only thing that matters. It sculpts everything. It's the reason the moon orbits the Earth orbits the sun orbits the center of the Milky Way, and the Milky Way drifts through a cosmic web of galaxy clusters that stretches across billions of light years. Every structure in the cosmos, from the smallest moon to the largest supercluster, exists because gravity pulled matter together and held it there. Isaac Newton figured out the basic rules in 1687 in what might be the most important book ever written, the Principia Mathematica. Before Newton, people had no unified picture of how things moved. The heavens and the earth seemed to operate under completely different rules. Up there, the planets traced perfect circles, or so people believed, through the celestial sphere, obeying divine geometry. Down here, objects fell, rivers flowed, and cannonballs arced through the air, according to messier, more terrestrial principles. The two realms were separate. Earthly mechanics and celestial mechanics were different subjects, taught by different scholars, governed by different logic. Newton said no. It's the same force. The apple falls because the Earth pulls on it. The moon orbits because the Earth pulls on it. The only difference is the moon has enough sideways speed that it keeps missing the ground. If you could throw the apple fast enough, it would orbit too. Same force, same rules, different circumstances. That unification, the realization that the cosmos and the kitchen are governed by the same law, was perhaps the most important insight in the history of science. And Newton gave us a formula. The gravitational force between two objects depends on their masses multiplied together, divided by the square of the distance between them. Double the mass, double the pull. Double the distance, the pull drops to a quarter. Simple, clean, and spectacularly useful. With that formula, you could predict eclipses, calculate the orbits of comets, figure out the tides. It was one of the greatest intellectual achievements in human history, and for more than 2 centuries, it seemed like the last word on the subject. But Newton's formula also lets you calculate something else, something that a few people in the 18th century started thinking about: escape velocity. If you throw a ball straight up, gravity pulls it back down. Throw it faster, it goes higher before falling back. There's a speed, a precise speed, where the ball would go up and never come back. It would have just enough kinetic energy to overcome the gravitational pull entirely. For the Earth, that speed is about 7 miles per second, roughly 25,000 miles per hour. For the Sun, it's much higher, about 383 miles per second. The more massive and compact the object, the higher the escape velocity. Now, here's where the story truly begins. In 1783, a man named John Michell is sitting somewhere in Yorkshire, England, thinking about light and gravity. Michell is one of those people that history has treated unfairly. He was genuinely brilliant, a polymath in the best sense, curious about everything, good at everything he touched. He was a clergyman by profession, a rector in the village of Thornhill. But his real passion was natural philosophy, what we would now call science. He did important work on earthquakes. He was the first person to suggest that earthquakes travel in waves. He was the first to propose that some double stars in the sky are not just visual coincidences, two stars that happen to lie along the same line of sight, but actual physical pairs, orbiting each other. He invented the torsion balance, a delicate instrument for measuring extremely weak forces, which Henry Cavendish later famously used to measure the gravitational constant and effectively weigh the Earth. Michell was a careful, rigorous thinker, and one day he started thinking about what would happen if you combined two ideas that everyone already knew. The first idea: gravity pulls on everything that has mass. The second idea: light travels at a finite speed. At the time, most scientists thought of light as being made of tiny particles, little corpuscles. Newton himself had favored this view.
If light is made of particles, Michell reasoned, then those particles have some kind of mass, or at least they behave as if they do. And if they have mass, then gravity should pull on them, just like it pulls on everything else. So Michell asked a question, a beautifully simple, beautifully dangerous question. What if a star was so massive and so dense that its escape velocity exceeded the speed of light? Think about what that means. Light particles fly off the surface of a star. Gravity pulls them back. Normally, light is fast enough to escape easily. The escape velocity from the surface of our Sun is about 383 miles per second, and light travels at roughly 186,000 miles per second, so light escapes the Sun without breaking a sweat. But Michell saw that this isn't guaranteed forever as you scale things up. If you make the star massive enough and dense enough, the escape velocity climbs. Eventually, it catches up with the speed of light. And then what? If the escape velocity at the star's surface is higher than the speed of light, then the light particles would be pulled back down, just like a ball thrown too slowly falls back to Earth. They'd arc upward, slow, stop, and fall back to the surface. The star would still be there. It would still have all its mass, still pull on things with its gravity. Nearby objects would feel its gravitational influence just as strongly as they'd feel the pull of any ordinary star of the same mass at the same distance. But no light would ever leave its surface. It would be invisible, dark, a star you could weigh but never see. Michell called these objects dark stars. He calculated that a star with the same density as our Sun, but about 500 times its diameter, would be massive enough for the escape velocity to exceed the speed of light. That works out to a star roughly 430 million miles across, far larger than Earth's entire orbit around the Sun. An enormous, unfathomably heavy star.
but one that Michell thought was at least conceivable. He even proposed a method for detecting such objects. You couldn't see them directly by definition, but if a dark star had a visible companion, an ordinary star orbiting around it, you could infer the dark star's presence from the companion's motion. You'd see a star wobbling back and forth, orbiting around something invisible, and from the wobble you could estimate the invisible object's mass. This is remarkably prescient. It's almost exactly the technique that would be used 2 centuries later to detect the first real black hole candidates. Michell wrote up this idea in a paper and sent it to the Royal Society, where it was read in 1783 and duly published. And then, essentially, nothing happened. People noted it. Henry Cavendish received the paper. It existed in the record. But it didn't catch fire. It didn't launch a research program or inspire a generation of follow-up work. It was a clever idea, acknowledged and then, more or less, shelved. About a decade later, independently, the great French mathematician Pierre-Simon Laplace arrived at essentially the same conclusion. Laplace was one of the towering intellects of his era, a man who had made massive contributions to celestial mechanics, probability theory, the mathematical description of the solar system. In 1796, in his book Exposition du système du monde, he included a passage about the possibility of invisible stars, bodies so massive that their escape velocity would exceed the speed of light. He even included it in the first 2 editions, and then he quietly removed it from the later editions. Just took it out. Why? Because by that point, the understanding of light was changing. In 1801, Thomas Young's double-slit experiment had provided strong evidence that light behaves as a wave, not a particle. And if light is a wave, the whole argument falls apart. Gravity pulls on particles, on things with mass. Waves are different. You don't grab a wave and drag it back down. The physical basis for the dark star idea evaporated, and Laplace, being Laplace, recognized that the argument no longer stood on solid ground. So the idea of a star so massive that light couldn't escape went dark itself. It disappeared from the scientific conversation for more than a century. 130 years of silence. The concept was technically still there, recorded in Michell's paper, mentioned in historical footnotes. But nobody was working on it. Nobody thought it pointed toward anything real. It was a curiosity from an era of physics that had been superseded, like alchemy's transmutation of lead into gold, an interesting historical idea that had been overtaken by a better understanding of the world. And here's what I find beautiful about that. The hidden truth about gravity, the fact that it could, under extreme enough conditions, trap light itself. That truth didn't go away just because people stopped looking at it. It was still there, embedded in the structure of the universe, waiting patiently in the mathematics, indifferent to whether anyone was paying attention. The universe didn't care that Laplace removed the passage from his book. The physics was the physics. The dark stars were a consequence of gravity and light, and no amount of human disinterest could change that. The idea just needed a different framework, a completely new way of thinking about gravity to bring it back into view. The universe, it turns out, is very patient with us. It doesn't rush its truths. It just waits for us to develop the tools to see them. And that framework was coming. It would arrive in 1915, from a man in Berlin who was about to rewrite everything anyone thought they knew about space, time, and the nature of gravity itself. A man who would struggle for nearly a decade to find the right equations, who would go down wrong paths and publish results he had to retract, who would have to teach himself an entirely new branch of mathematics
because the math he already knew wasn't powerful enough to express what his physical intuition was telling him. And when he finally got it right, within weeks, a solution would arrive from the most improbable place imaginable. A solution that contained, buried deep in its mathematics, the ghost of Michel's dark star. Only now, it would be something far stranger, far more radical, and far more unsettling than anything an 18th century clergyman could have imagined. Albert Einstein. You've heard of him. Of course you have. Everyone has. The wild hair, the chalkboard equations, the tongue sticking out in that famous photograph. He's become a cultural icon, a shorthand for genius itself. And because of that, his story often gets compressed into something too neat, too simple. The absent-minded professor who just saw things other people couldn't. A bolt from the blue, a flash of inspiration, and suddenly the universe was explained. The reality was so much harder than that, so much more human. And understanding how hard it actually was matters for this story. Because what Einstein built, the theory of general relativity, is the foundation on which everything we know about black holes rests. Without it, there are no event horizons, no singularities, no Hawking radiation, no information paradox. Everything flows from general relativity. So let's spend some time with how it came together.
Einstein had already shaken physics to its foundations in 1905, his miracle year, when he published 4 extraordinary papers while working as a clerk in the Swiss Patent Office. One of those papers introduced special relativity, which dealt with objects moving at constant speeds and showed that space and time are woven together into a single fabric, that the speed of light is the same for all observers, and that strange things happen to time and length and mass when you approach that speed. Matter and energy are interchangeable. E equals mc squared. The world had never seen anything like it. But special relativity had a gap in it, and Einstein knew it. It only worked for observers moving at constant velocities, in the absence of gravity. It didn't say anything about acceleration or gravitational fields. And gravity was the dominant force in the universe. If you wanted a complete picture of reality, you needed to bring gravity into the framework.
Einstein started working on this around 1907, and it consumed him for the next 8 years. The key insight came early, and it was physical, not mathematical. Einstein called it the happiest thought of his life. He imagined a man falling from a roof. While falling, the man would feel weightless. He wouldn't feel gravity pulling on him at all. Everything in his immediate vicinity would be falling alongside him, his hat, his pocket watch, his keys, all of them accelerating downward at the same rate. From the falling man's perspective, gravity has vanished. He's floating, weightless, as if he were drifting in empty space, far from any planet or star. That thought, that image of a falling man, led Einstein to what he called the equivalence principle. The idea that gravitational acceleration and ordinary acceleration are, locally, indistinguishable. If you're in a closed room with no windows, you can't tell whether you're standing on the surface of the Earth, feeling gravity pull you down, or in a rocket ship, accelerating upward at the same rate. The physics inside the room is the same either way. This might sound like a philosophical curiosity, but Einstein realized it had profound consequences. If gravity and acceleration are equivalent, and if acceleration can affect the behavior of light, which special relativity showed it could, then gravity must affect light too. Light should bend in a gravitational field. Clocks should tick more slowly in stronger gravity. Gravity should change the wavelength of light,
stretching it toward the red end of the spectrum as it climbs out of a gravitational well. These were testable predictions, and they would all eventually be confirmed. But the equivalence principle was just the starting point, the physical intuition. To turn it into a full theory, Einstein needed mathematics, and the mathematics he needed didn't come easily. He had to learn an entirely new branch of math, tensor calculus, the geometry of curved spaces developed by Bernhard Riemann and others in the 19th century. This was far beyond anything Einstein had worked with before. He was a physicist trying to teach himself the most abstract mathematics of his time, because the math he already knew wasn't powerful enough to express what his physical intuition was telling him. There were years of wrong turns. In 1913, Einstein and his mathematician friend Marcel Grossmann published a theory, the Entwurf theory, that they thought was the answer. It wasn't. It had subtle mathematical flaws that took Einstein months to find. He presented work at conferences that he later had to retract. He corresponded with the great mathematician David Hilbert, and there's a complicated historical question about who arrived at the correct equations first, though the physical insight was unquestionably Einstein's. Finally, in November 1915, Einstein presented the final version of his field equations to the Prussian Academy of Sciences in Berlin. He presented them over a series of 4 Thursday lectures, and the final lecture, on November 25th, contained the correct equations. Years later, he described the feeling of completing the theory as heart palpitations. He told a friend that he was beside himself with excitement. For a man who cultivated an image of cool, detached intellectual clarity, Einstein's private letters from that month reveal something closer to ecstasy. He had spent 8 years building this thing, years of frustration and dead ends and self-doubt, and now it was done, and it was beautiful. And the equations were astonishing. They said that mass and energy don't just sit inside space-time like objects on a table. They curve space-time itself. The presence of matter bends the geometry of the universe around it, and other objects then move along the curves created by that bending. Gravity, in this picture, isn't a force at all. There's no invisible rope reaching from the sun to the Earth, pulling the planet inward. Instead, the sun's mass curves the space-time around it, and the Earth follows the most natural path through that curved geometry. It's falling, in a sense, but falling along a curve that wraps around and around, and that curved path is what we call an orbit. The rubber sheet analogy you've probably heard, the one where you put a bowling ball on a stretched membrane and it sags, that captures some of the idea. But it's misleading in an important way. It shows the curvature of space, but general relativity is about the curvature of space-time, space and time woven together. The analogy also has a more basic problem. It uses gravity. The bowling ball sags because gravity pulls it down to explain gravity, which is a bit circular. Still, as a way to get the basic intuition across, it works well enough. Mass warps the space around it. Other objects follow the curves in that warped space, and the result looks, from our everyday perspective, like a force pulling things together. But really, nobody is pulling anybody. Objects are just following the most natural paths through a landscape that has been shaped by the presence of mass and energy. Einstein's equations describe this with extraordinary precision. They tell you, given any distribution of mass and energy, exactly how space-time curves, and given any curvature of space-time, exactly how objects move. The equations are written in a compact, elegant notation, but solving them for any realistic situation is ferociously difficult. They're 10 coupled, nonlinear partial differential equations, and finding exact solutions that can be written down in closed form, is rare and hard. And the time part matters enormously. Near a massive object, time itself runs slower. A clock sitting on the surface of the Earth ticks slightly slower than a clock floating in empty space far from any mass. This effect is tiny for everyday objects, but it's measurable. The GPS satellites orbiting the Earth have to correct for it. The clocks on the satellites tick slightly faster than clocks on the ground because they're further from Earth's mass, and the space-time up there is slightly less curved. If you didn't account for this correction, GPS would accumulate positioning errors of about 6 miles per day. Every time you use your phone to navigate, you're relying on Einstein's general relativity to get you to the right address. And near a sufficiently massive, sufficiently compact object, this time dilation becomes extreme.
Time doesn't just slow down a little, it slows down a lot. Near the surface of a neutron star, clocks tick about 20 to 30% slower than they do far away. Near the event horizon of a black hole, the effect approaches infinity. A clock hovering just above the horizon would, from the perspective of a distant observer, appear to tick more and more slowly, approaching zero, seeming to freeze entirely as it nears the boundary. We'll come back to that, because this time dilation is central to understanding what black holes actually are and why they are so deeply strange. Einstein knew his equations were difficult. Solving them exactly for any realistic situation, finding the precise shape of space-time around a given distribution of mass and energy, was a formidable mathematical challenge. He expected it would take years, maybe decades, for people to find exact solutions.
He was working on approximate solutions himself, using clever tricks to extract predictions like the bending of starlight and the shift in Mercury's orbit, without solving the full equations directly. Which is why what happened next surprised him so much. Within weeks of the field equations being published, a solution arrived. An exact, complete, elegant solution. And it came from the last place anyone would have expected. Karl Schwarzschild was a German physicist and astronomer, 41 years old. He was one of those rare scientists who was excellent at both theory and observation. He had directed the Astrophysical Observatory in Potsdam. He had done important work on stellar atmospheres, on photographic optics, on the transfer of radiation through gases. He was deeply respected in the German physics community. And in 1915, Karl Schwarzschild was on the Eastern Front of World War I, serving as a volunteer in the German army.
He was calculating artillery trajectories in Russia. He was already ill with pemphigus, a painful autoimmune disease that causes severe blistering of the skin and mucous membranes. It would kill him within months. And there, in the middle of a war, between the cold and the shells and the disease, Schwarzschild got hold of Einstein's newly published papers. He read the field equations, and he solved them for the simplest possible case, the space-time around a perfectly spherical, non-rotating mass, a single dense ball of matter sitting in otherwise empty space. He sent his solution to Einstein in a letter in December 1915. Einstein presented it to the Prussian Academy in January 1916, and Karl Schwarzschild died on May 11, 1916, at the age of 42. He never saw the full implications of what he had found. I want you to sit with that for a moment.
The first exact solution to the most important equations in modern physics, the solution that would eventually lead to the prediction of black holes, was worked out by a dying man in a war zone and sent to the author in a letter. The letter itself is a visible artifact. You can look it up. Schwarzschild's handwriting, his calculations, posted from the Eastern Front. But what was hidden inside those calculations, buried in the mathematics, would take decades to fully understand. Because Schwarzschild's solution was beautiful and troubling in equal measure. In the regions far from the central mass, it behaved exactly as you'd expect. It reproduced Newtonian gravity as an approximation. It predicted the bending of light around massive objects. It gave the correct shift in Mercury's orbit. Everything checked out. But the solution also contained something deeply strange. At a particular distance from the center, a specific radius that depended on the mass of the object, one of the terms in the equation went to infinity. The mathematics blew up. For an object with the mass of our Sun, this critical radius was about 2 miles. For the Earth, it would be about 9 millimeters, roughly the size of a marble. And inside that radius, the mathematics did something even more disturbing. The roles of space and time appeared to swap. The coordinate that had been measuring distance from the center started behaving like a time coordinate. The coordinate that had been measuring time started behaving like a spatial direction. What this meant, though it would take physicists decades to understand it properly, was that inside this boundary, moving forward in time and moving inward toward the center became the same thing. You could no more stop yourself from moving toward the center than you can stop yourself from moving into next Thursday.
That critical radius is what we now call the Schwarzschild radius, or the event horizon. And the idea it implied was this: if you could somehow compress all the mass of the Sun into a sphere just 2 miles across, space-time would curve so severely at that surface that nothing, not light, not any signal, could ever escape from inside it. But almost nobody took this seriously as a physical possibility. Not in 1916. Not even Schwarzschild himself, as far as we can tell. The prevailing attitude was that this was a mathematical curiosity, an artifact of the equations that would never correspond to anything in the real universe. Stars are enormous. The Sun is nearly 870,000 miles across. The idea that anything in nature could be compressed to a ball 2 miles wide seemed absurd. Surely there was some physical process, some pressure, some force that would always prevent matter from collapsing that far. Einstein himself thought so.
He spent years trying to prove that the singularity in Schwarzschild's solution was not physical, but merely an artifact of the coordinate system being used. He was partially right about that, actually. In a very specific technical sense, the event horizon itself is what physicists call a coordinate singularity, a place where the chosen coordinate system breaks down, but the underlying physics is smooth. A distant observer sees infinity at the horizon because their coordinates can't properly describe that boundary, not because the physics there is actually infinite. It's a bit like how a map of the Earth has trouble at the poles, not because there's anything wrong with the poles, but because the map projection can't handle them cleanly. But the singularity at the very center, the point where the density truly goes to infinity, that was a genuine physical prediction of the equations. And Einstein didn't like it. He published a paper in 1939 explicitly arguing that matter could not collapse past the Schwarzschild radius, that some physical process would always prevent it. He was wrong about that, as it turned out. But he was Einstein, and his opinion carried enormous weight. So Schwarzschild's solution sat there, visible in the published literature, available to anyone who cared to read it. But its most radical implication, the possibility that objects could exist in nature from which nothing, not even light, could escape, remained hidden, dismissed, actively resisted by many of the smartest people in the world. The visible part of the story, Einstein's triumphant theory, his celebrity, his equations confirmed by the bending of starlight during the 1919 eclipse. All of that was front-page news. The hidden part, the dark object lurking in Schwarzschild's mathematics, the letter from the trenches, the dying man's gift to physics, that stayed in the shadows.
For now. Because someone was about to do something that would drag the hidden truth closer to the surface. something that would make it much harder to ignore. And that someone was a 19-year-old kid on a steamship, crossing the ocean from India to England, with a notebook full of calculations that would change everything. His name was Subrahmanyan Chandrasekhar, and the brilliant, terrible thing about his story is that he was right, completely right, and the most powerful person in his field destroyed him for it. Here's what you need to understand about stars before we can understand what Chandrasekhar figured out on that ship. A star is a balancing act. Every star, including our sun, exists because two forces are locked in a tug-of-war. On one side is gravity, pulling everything inward, trying to crush the star down to the smallest possible size.
On the other side is pressure, the outward push of hot gas and radiation, generated by the nuclear fusion reactions blazing in the star's core. Hydrogen atoms slamming into each other at millions of degrees, fusing into helium, releasing enormous amounts of energy. That energy heats the gas pushes outward, and gravity pushes inward. And for most of a star's life, the two sides are locked in a stable equilibrium. The star shines steadily, neither expanding nor contracting, burning through its fuel at a controlled rate. But stars don't burn forever. They have a finite supply of fuel, and when that fuel runs out, the balance breaks. The outward pressure fades, and gravity begins to win. The star contracts, shrinking under its own weight, and the critical question that would define this entire chapter of the black hole story is, what happens next? Is there always something that catches the star? Some new source of pressure that halts the collapse and creates a stable remnant? Or could a star, under the right circumstances, just keep falling inward, past every possible defense, with nothing to stop it? By the late 1920s, physicists had a partial answer. A British physicist named Ralph Fowler had shown that when an ordinary star like the Sun runs out of nuclear fuel and contracts, it doesn't just collapse into nothing, it shrinks down into a very dense, very compact object called a white dwarf. And white dwarfs are held up by something fundamentally different from the radiation pressure that supports a living star. They're held up by a quantum mechanical effect called electron degeneracy pressure. Let me explain this because it's actually one of the most beautiful ideas in physics, and it matters enormously for the black hole story. In quantum mechanics, there's a rule called the Pauli exclusion principle. It says that no two electrons can be in exactly the same quantum state at the same time. They can't share the same location and the same momentum and the same spin simultaneously. Something has to be different. If you try to squeeze electrons into a smaller and smaller space, they resist because the available quantum states get used up. Some of the electrons are forced into higher energy states, forced to move faster, and that creates a pressure. Not a thermal pressure, not a pressure from heat or radiation, but a purely quantum mechanical pressure arising from the fundamental rules governing how particles are allowed to exist. Fowler showed that this electron degeneracy pressure is what supports a white dwarf against gravitational collapse. A star dies, contracts, squeezes its electrons into a smaller and smaller volume, and the degeneracy pressure kicks in and holds it up. The star settles into a new, much denser equilibrium. A white dwarf might contain the mass of the Sun packed into a sphere the size of the Earth. A teaspoon of its material would weigh about 5 tons. But it's stable. Gravity is held at bay. There's a floor. Everything is fine. And this is where a 19-year-old kid on a steamship comes into the story. Subrahmanyan Chandrasekhar, Chandra as everyone called him, was born in Lahore in 1910, in what was then British India. He came from a family of exceptional intellectual caliber. His uncle, C.V. Raman, would win the Nobel Prize in Physics in 1930 for his work on light scattering. Chandra himself was clearly brilliant from a young age, the kind of student who didn't merely master his courses but pushed past them, reading original research papers as a teenager, publishing his first scientific paper at 18. In 1930, at the age of 19, Chandra boarded a ship from Bombay bound for England. He had won a government scholarship to study at Cambridge under Ralph Fowler, the very man who had worked out the physics of white dwarfs. The voyage took weeks, long, slow days on the open ocean, and Chandra used that time to think. What he was thinking about was Fowler's white dwarf theory, and specifically, he was thinking about what happens when you add special relativity to the picture. Fowler had done his calculations using ordinary, non-relativistic quantum mechanics. But Chandra realized that in a very dense white dwarf, where the electrons are packed so tightly that the degeneracy pressure forces some of them to move at nearly the speed of light, you need to use special relativity. And when you do, something changes, something fundamental. In the non-relativistic case, the degeneracy pressure increases fast enough to always keep up with gravity. Squeeze the star smaller, the pressure rises, and eventually equilibrium is restored.
But when the electrons become relativistic, moving at speeds close to the speed of light, the pressure doesn't increase as quickly. The mathematical relationship between density and pressure changes. And Chandra, working through the calculations in his notebook as the ship crossed the Indian Ocean, discovered that there's a limit, a maximum mass above which electron degeneracy pressure simply cannot support a white dwarf against gravitational collapse. That limit, which we now call the Chandrasekhar limit, is about 1.4 times the mass of the Sun. Below that mass, a white dwarf is stable. Gravity and degeneracy pressure are in balance. The star sits there quietly, slowly cooling, slowly fading, but structurally intact, potentially for longer than the current age of the universe. Above that mass, degeneracy pressure loses the fight. It's not strong enough. Gravity wins. And Chandra realized what that meant.
If a dying star's remnant is more massive than 1.4 solar masses, there is no stable white dwarf configuration. The flaw that Fowler had found doesn't exist for heavy enough stars. Gravity breaks through, and the star must continue to contract. Chandra arrived in England with this result, refined it over the following years, and by 1935, he was ready to present it to the Royal Astronomical Society in London. He was 24 years old. He had been working on this problem for 5 years. He was thorough. He was careful. His mathematics was airtight. And what happened next is one of the most painful episodes in the history of science. Arthur Stanley Eddington rose to speak. Eddington was, at that moment, arguably the most famous astrophysicist in the world. He was the man who had led the expedition to observe the 1919 solar eclipse, the expedition that confirmed Einstein's prediction that gravity bends light.
He was the foremost authority on the internal structure of stars. He was brilliant, charismatic, and enormously influential. When Eddington spoke, the astronomical community listened. And Eddington got up after Chandrasekhar's presentation and publicly, devastatingly, mockingly, rejected the entire result. He didn't just disagree with the mathematics, he dismissed the physical conclusion as absurd. He argued that it was impossible for nature to allow a star to collapse past the white dwarf stage. There had to be some mechanism, some law of nature that would prevent it. He invoked a kind of aesthetic argument. The universe couldn't be that messy, that unruly. Stars must have a dignified retirement. They must settle down into stable, finite remnants. The idea that they might just keep collapsing, shrinking without limit, was, in Eddington's view, a reductio ad absurdum. a conclusion so ridiculous that it proved the starting assumptions must be wrong.
The language Eddington used was cutting. He spoke of absurdity and stellar buffoonery. He suggested that there ought to be a law of nature preventing stars from behaving in such an undignified manner. And the way he delivered it, from his position of supreme authority, with the full weight of his reputation and his rhetorical skill, was devastating to a young physicist presenting his life's work. The room sided with Eddington. Not because his arguments were stronger, because they weren't, but because he was Eddington. His authority was immense. His personality dominated the field. Challenging him was career suicide. And Chandra, 24, Indian, relatively unknown, with a heavy accent and no institutional power base, was no match for that kind of social and professional force. Years later, other physicists would acknowledge privately that Chandrasekhar had been right all along.
Leon Rosenfeld, who was present at the meeting, later described Eddington's behavior as pathological. But at the time, in the room, nobody stood up for Chandra. Nobody said, "Wait, let's look at the mathematics again." The social dynamics of the scientific community, the deference to authority, the reluctance to challenge a great man publicly, all of these invisible forces conspired against the visible truth of the equations. Think about what was visible in that room and what was hidden. The visible spectacle was a great man of science rendering his verdict. The hidden reality was that a young physicist had found an important truth, a truth that would eventually be confirmed in every detail, and was being punished for it. The mathematics was right. The physics was right. And the most powerful person in the field decided that the conclusion was too disturbing to accept. Chandrasekhar was devastated. He later described the experience as deeply humiliating, though he rarely spoke about it in public. In private correspondence, he was more forthcoming. He felt that Eddington had not engaged with his mathematics at all, but had simply refused to accept the conclusion on emotional grounds. And he was right about that. Eddington never identified a mathematical error in Chandra's work, because there wasn't one. He simply couldn't accept a universe in which stars collapse without limit. Chandra didn't give up science, but he left the field of stellar structure. He moved to America, took a position at the University of Chicago, and spent the rest of his career working on other problems, making important contributions to many areas of astrophysics: radiative transfer, hydrodynamic stability, ellipsoidal figures of equilibrium, the mathematical theory of general relativity itself. He was prolific and brilliant across multiple fields. He would win the Nobel Prize in 1983, partly for the work Eddington had ridiculed almost 50 years earlier. There is a poignancy to that. Chandra got his recognition eventually, but the delay cost the field decades. If his result had been accepted in 1935, the next questions, what happens beyond the white dwarf limit? Is there a neutron star limit? What lies beyond that? Would have been asked sooner. The whole trajectory of black hole physics might have been accelerated by a generation. Instead, the question of what happens to stars too massive for the white dwarf floor was effectively shut down in the English-speaking physics community for nearly 2 decades. The hidden truth, the fact that massive enough stars have no stable endpoint, that gravity will eventually overwhelm every form of pressure we know of, that truth went underground. Chandra knew it was there. A few others suspected it. But the visible story, the story that most physicists accepted, was Eddington's story. Nature would find a way to prevent total collapse. There had to be a flaw. Somewhere. Was there? Was there some deeper level, some new form of pressure, some last line of defense that gravity couldn't breach? The answer to that question would come from a place you might not expect. From nuclear physics, from the newly discovered neutron, from a physicist who was about to calculate the ultimate limits of matter under compression. And the answer would turn out to be, yes, there is one more flaw. But it has a limit too. And beyond that limit, there is nothing. Beyond that limit, gravity wins, absolutely, and forever. And the man who would prove this, who would write the paper showing that a sufficiently massive star must collapse past every possible barrier and form exactly the kind of object Schwarzschild's mathematics had predicted, would publish his proof on the most catastrophic day in 20th century history. And then he would walk away from the problem entirely, consumed by a very different kind of physics, and the proof would sit unread, gathering dust for 20 years. The neutron was discovered in 1932 by James Chadwick at Cambridge. It was a particle with almost the same mass as a proton, but no electric charge, and its discovery immediately opened a new possibility for what might lie beyond the white dwarf. If you squeeze matter hard enough, past the density where electrons hold things up, you enter a regime where the electrons and protons are forced together to form neutrons. The star becomes a ball of neutrons, a neutron star, incredibly dense, a teaspoon of its material weighing about 1 billion tons. And neutron degeneracy pressure, the same quantum mechanical effect that supports a white dwarf, but now arising from neutrons instead of electrons, would hold it up against further collapse. Two physicists, Walter Baade and Fritz Zwicky, proposed the existence of neutron stars in 1934, just 2 years after the neutron itself was discovered. They even suggested that neutron stars might form in supernovae, the spectacular explosions of massive stars. Zwicky, in particular, was a colourful and combative figure, known for calling his colleagues spherical bastards, because, he said, they were bastards from every angle. He was also frequently ahead of his time. He predicted neutron stars, named supernovae, proposed dark matter, and was right about all three, decades before the mainstream physics community caught up. So the picture after the early 1930s looked like this. A dying star sheds its outer layers. If the remaining core is below the Chandrasekhar limit, about 1.4 solar masses, it settles into a white dwarf, held up by electron degeneracy pressure. If the core is more massive than that, it collapses further. The electrons are squeezed into the protons to form neutrons, and the star becomes a neutron star, held up by neutron degeneracy pressure. There's a deeper flaw. Gravity gets caught again. Crisis averted. But the obvious next question hangs in the air, doesn't it? Does the neutron star flaw have a limit too? And this brings us to a man whose name you almost certainly know, though probably for very different reasons. J. Robert Oppenheimer. Oppenheimer was a peculiar figure. Brilliant, cultured, charismatic, fluent in 6 languages, he read Sanskrit for pleasure and quoted Hindu scripture in casual conversation. He was tall and gaunt, a chain smoker who sometimes forgot to eat. And he had a mind that could hold multiple complex ideas in tension simultaneously, in a way that few of his contemporaries could match. He was also deeply ambitious, occasionally arrogant, and possessed of a poetic streak that would lead him years later to describe the first nuclear detonation with the words, "Now I am become death, the destroyer of worlds." But in the late 1930s, before the war consumed everything, Oppenheimer was doing some of the purest, most profound theoretical work of his career. And it was about gravity. Working with his student George Volkoff, Oppenheimer answered the neutron star question in 1939. They calculated the structure of neutron stars using general relativity, because at the densities involved, Newtonian gravity is no longer accurate enough. And they found exactly what you might now be expecting. There is a maximum mass for neutron stars,
just as there is for white dwarfs. The exact number was hard to pin down because the physics of nuclear matter at those extreme densities was poorly understood. But it fell somewhere in the range of 2 to 3 solar masses. Beyond that mass, even neutron degeneracy pressure fails. And then, in a paper that is one of the most remarkable and overlooked documents in 20th century physics, Oppenheimer and a different student, Hartland Snyder, asked the question that nobody wanted answered. What happens to a star that exceeds even the neutron star limit? What happens when there is no floor left? They published their answer on September 1st, 1939, the same day that German tanks rolled into Poland and the Second World War began. The timing is almost too dramatic to be real. While the world was plunging into the most devastating conflict in human history, two physicists in California quietly published a proof that the most devastating force in the universe, gravity, has an absolute victory condition. Given enough mass, gravity beats everything. There is no last resort, no hidden mechanism, no emergency brake. A sufficiently massive star that exhausts its fuel will collapse through the white dwarf stage, through the neutron star stage, and continue falling, shrinking, compressing, past the Schwarzschild radius, past the point of no return, and all the way down to a singularity, a point of infinite density where the equations of general relativity break apart and physics, as we understand it, ceases to make sense. Oppenheimer and Snyder had proven the existence, in principle, of what we would eventually call a black hole.
And they had done something else extraordinary. Something that would later turn out to be one of the most important insights in the entire history of the subject. They showed that the collapse looks completely different depending on who is watching. Imagine you are standing far away, safely distant from the collapsing star. What do you see? You see the star shrinking, getting smaller and denser. As its surface approaches the Schwarzschild radius, the light coming from it gets more and more redshifted. The photons have to climb out of an increasingly deep gravitational well, and they lose energy doing so, stretching to longer and longer wavelengths. The star grows dimmer. It also appears to slow down. From your distant vantage point, the surface seems to approach the Schwarzschild radius more and more slowly, asymptotically, never quite reaching it.
The star fades from view, getting redder and dimmer and slower, until the last photons stretch to infinite wavelength and the star winks out of the visible universe entirely. From the outside, the star doesn't crash through the boundary in a dramatic instant. It fades away. It redshifts into silence. But now imagine you are riding on the surface of the collapsing star. Your experience is completely different. You don't notice anything special as you pass through the Schwarzschild radius. There's no wall there, no sign, no perceptible change. The geometry of space-time at the horizon is smooth. You pass through it the way you pass through any other point in space. You only discover you've crossed it when you try to send a signal outward and find that the signal never reaches anyone. Because now, inside the horizon, every direction you can possibly travel leads deeper inward. The singularity isn't a place in space that you can avoid by steering around it. Inside the event horizon, the singularity is in your future. It's a moment in time, and you can no more avoid it than you can avoid tomorrow. Two observers, watching the same event, see completely different things. For the distant observer, the collapse appears to freeze at the horizon, time seemingly stopping at the boundary. For the falling observer, the collapse happens quickly, smoothly, and ends in annihilation. Both descriptions are correct. Both are real. Neither is an illusion or an error. They are two equally valid perspectives on the same physical process, seen through different slices of curved space-time. And this gets at something deep about what a black hole really is. It's not just an object. It's a boundary in the structure of information itself. The event horizon is the surface that separates what the outside universe can know from what it cannot.
Everything inside that boundary is hidden, causally disconnected, permanently beyond the reach of any observation or measurement that an external observer could ever perform. And everything outside the boundary is visible, accessible, in principle measurable. The black hole doesn't hide its interior the way a locked safe hides its contents. A safe is sealed by human engineering. You could, in principle, pick the lock, drill through the walls, find a way in. A black hole is sealed by the geometry of space-time itself. There is no lock to pick. There is no wall to drill through. The interior is hidden not by any physical barrier, but by the fundamental structure of causality, the way cause and effect are organized in curved space-time. Going in is easy. Coming out is not impossible in the sense that it's very difficult. It's impossible in the sense that the word out no longer refers to a direction you can travel. This asymmetry between the visible and the hidden was built into the physics from the very beginning. From the outside, the black hole reveals almost nothing about its interior. From the inside, there is no outside anymore. The horizon is a one-way mirror on the grandest possible scale. The universe can look in, but nothing inside can look out. Oppenheimer and Snyder laid all of this out in 1939. They had, for the first time, a complete theoretical description of gravitational collapse to a black hole, the mechanism, the observable signatures, the experience of both external and infalling observers. It was one of the most profound results in general relativity since Einstein himself, and the world barely noticed. The paper appeared in the Physical Review on September 1st, the day the war started. Within weeks, the scientific community's attention was consumed by far more immediate concerns.
And Oppenheimer himself was about to be pulled into the most consequential military project of the 20th century. Within a few years, Oppenheimer was in Los Alamos, New Mexico, leading the Manhattan Project, directing the effort to build the atomic bomb. The man who had just proved that stars can collapse into objects of infinite density was now focused on splitting atoms apart. The irony is hard to miss. Both problems, nuclear fission and gravitational collapse, involve the deepest forces in nature, unleashed without limit. But one was a matter of wartime urgency, and the other was a question about the far future of dying stars. The choice was obvious, and Oppenheimer made it. After the war, Oppenheimer became one of the most prominent public intellectuals in America, involved in science policy, nuclear arms negotiations, eventually destroyed by the McCarthy-era loyalty hearings. He never returned to the problem of gravitational collapse.
The proof he had written, the hidden truth he had uncovered, sat in the journals essentially unread for 2 decades. Kip Thorne, who later became one of the great experts on general relativity, called this period the dark ages of black hole physics. And it's worth understanding why the neglect was so thorough, because it tells you something important about how science works, or sometimes doesn't. Part of it was the war itself. The war redirected the careers and attention of an entire generation of physicists. The people who might have followed up on Oppenheimer's result were building radar systems, designing bombs, developing nuclear reactors. After the war, many of them stayed in those applied fields or moved into the booming new area of particle physics, where the action was. Quantum electrodynamics, the quantum theory of the electromagnetic force, was being worked out with spectacular success by Feynman, Schwinger, and Tomonaga in the late 1940s.
It was the glamorous frontier, full of precise predictions and triumphant experimental confirmations. General relativity, by contrast, felt old-fashioned to many physicists. A beautiful theory with few practical applications and almost no experimental tests beyond the handful that had been done in the 1920s. Part of it was cultural. The British and American physics communities, where most general relativistic research had been concentrated, had been shaped by Eddington's aesthetic objection to gravitational collapse. Even after Eddington died in 1944, his influence persisted. The prevailing attitude was that singularities were mathematical pathologies, signs that the theory was being pushed too far, not predictions of actual physical objects. And part of it was simply that the mathematical tools for working with general relativity were underdeveloped.
The theory had been around since 1915, but the techniques for understanding its global structure, its causal properties, the behavior of geodesics and horizons and trapped surfaces, all of these would only be developed in the 1960s and 70s. Without those tools, the Oppenheimer-Snyder paper was a starting point with no clear path forward. 20 years. For 20 years, the physics community mostly ignored the question of what happens when a star collapses past every possible barrier. There were a few people who kept thinking about it, John Wheeler at Princeton for one, though Wheeler spent most of those years arguing that some unknown mechanism must prevent complete collapse. The Soviet physicists Yakov Zeldovich and Igor Novikov worked on the problem quietly, somewhat isolated from the Western physics community by the Iron Curtain.
But for most physicists in the 1940s and 50s, the hot topic was quantum electrodynamics, particle physics, the nuclear force. The frontier of physics had moved to the very small, and the question of what gravity does at its most extreme was considered by most either settled, nature prevents collapse, or irrelevant. Even if it happens, what can we learn from it? The hidden proof was there, published, peer-reviewed, technically accessible to anyone with a physics library. But the scientific community's attention was elsewhere, and without attention, even a correct proof can languish in obscurity. The truth about gravitational collapse waited in the dark, like the object it described. But 2 decades is not forever, and by the late 1950s and early 1960s, things were about to change. A new generation of physicists was arriving. Physicists who hadn't been through the war, who hadn't been scarred by the bomb, who were drawn to the grandest questions about the universe rather than the smallest. Radio telescopes and X-ray detectors were revealing a cosmos far more violent and energetic than anyone had suspected. Quasars, objects millions of times brighter than entire galaxies, were being discovered at enormous distances. Their energy output was staggering, and nobody could explain it. If these objects were as far away as their redshifts suggested, they were pouring out energy at rates that no known physical process could sustain. Unless there was a process that nobody had taken seriously. Unless there was an engine at the hearts of these distant beacons that ran on the most powerful fuel in the universe. Gravity itself. Unless matter was falling into something so massive, so compact, so deep a gravitational well that the energy released by the infall could outshine 100 billion stars. The idea was in the air, the observations were demanding an explanation, and the hidden proof, Oppenheimer's forgotten paper, was about to be rediscovered. All it needed was a name. The man who gave black holes their name didn't believe in them, not at first. John Archibald Wheeler was one of the great physicists of the 20th century.
a man of enormous intellect and even more enormous personality. He had worked on the atomic bomb during the war. He had done foundational work in nuclear physics. He was Richard Feynman's thesis advisor at Princeton, and for most of the 1950s, he was deeply skeptical that complete gravitational collapse was possible. He kept looking for a way out, some mechanism, some undiscovered physical process that would prevent a massive star from crossing its own Schwarzschild radius. Wheeler was not being foolish. His instinct that nature should prevent infinite compression was shared by most physicists of his generation. The idea of a point of infinite density, a place where the known laws of physics break down entirely, seemed more like a failure of the theory than a prediction of reality. When your equations give you infinity, it usually means you've pushed them past the point where they're valid. And Wheeler, with his deep experience in both nuclear physics and general relativity, wanted to find the physical mechanism that would step in before the equations went haywire. He didn't find it. Through the late 1950s, he and his students worked through every possibility they could think of. Could the star shed enough mass through radiation to drop below the critical limit? The calculations said no, not always. Could nuclear forces become repulsive at extreme densities and create a new kind of pressure floor? The physics didn't support it. Could quantum effects at the Planck scale, the smallest possible scale in nature, somehow prevent the formation of a singularity? Maybe, but nobody knew how to calculate at the Planck scale, and the classical result was clear. General relativity predicted complete collapse, full stop. And so, gradually, reluctantly, with a kind of grudging respect for the mathematics, Wheeler came around. By the early 1960s, he accepted that complete gravitational collapse was physically possible, and once he accepted it, he threw himself into the problem with his characteristic energy and flair, transforming from the idea's most prominent skeptic into one of its greatest champions and communicators. And what helped push Wheeler and many others over the edge was the sky itself. Because while the theorists had been arguing about whether complete collapse was possible, the observers had been finding things in the universe that desperately needed an explanation. In 1963, astronomers discovered quasars. These were point-like sources. They looked like stars, but their spectra showed enormous redshifts, meaning they were fantastically distant, billions of light-years away. And if they were that far away, and yet still visible, the amount of energy they were producing was staggering. A single quasar could outshine an entire galaxy, hundreds of billions of stars, from a region that appeared to be tiny. No known physical process could explain that kind of energy output from that small a volume. Nuclear fusion, the process that powers stars, was nowhere near efficient enough. But gravitational energy was.
If matter were falling into an incredibly deep gravitational well, spiraling inward, heating up, radiating energy as it fell, you could, in principle, extract enormous amounts of energy from a very compact region. The efficiency of gravitational accretion, the fraction of the rest mass energy that gets converted to radiation, can be 10 or 20 times higher than nuclear fusion. A supermassive object, millions or billions of solar masses, sitting at the center of a galaxy, actively pulling in gas, could power a quasar. And the most natural candidate for such a supermassive, ultra-compact object was exactly the kind of thing that Oppenheimer and Snyder had predicted in 1939. A completely collapsed object, a gravitational singularity surrounded by an event horizon, a black hole. The quasar discovery didn't prove that black holes existed, but it created an urgent need for them. The universe was waving a visible clue, an extraordinarily bright clue, and saying, I need you to take gravitational collapse seriously. The old arguments about whether nature would really allow such objects felt less convincing when the sky was full of beacons that seemed to demand them. It was Wheeler who, in 1967, at a conference in New York, first used the term black hole. At least, that's the widely accepted story. Wheeler himself sometimes said that a member of the audience suggested it, and he simply adopted it. Either way, the name stuck instantly. Before Wheeler, these objects had been called frozen stars or collapsed stars or singularities or dark stars, and none of those names had captured the public imagination. Black hole was vivid, evocative, slightly ominous, and immediately comprehensible. You hear it and you know at some intuitive level what it means. A hole in space. A place where things go in and don't come out. A place of absolute darkness.
The name was a visible act, a public moment, a branding decision that changed the cultural trajectory of an entire field of physics. But behind that visible moment, a hidden revolution had been underway for several years. A revolution in the mathematical understanding of what these objects actually were. The key figure in that revolution was Roger Penrose. Penrose is a mathematician as much as a physicist, and that's important for understanding what he contributed. The earlier arguments about gravitational collapse, from Oppenheimer and Snyder in '39, and from others who had worked on the problem since, all relied on simplifying assumptions. They assumed perfect spherical symmetry, a perfectly uniform star collapsing in a perfectly even way. And that raised a legitimate objection. Real stars aren't perfectly spherical. Real collapses aren't perfectly uniform. Maybe the singularity only appeared in the mathematics because the simplifying assumptions forced it. Maybe a real, lumpy, irregular collapse would behave differently. Maybe the infalling matter would miss the center, bounce off itself, swirl around, and avoid forming a singularity altogether. This objection had been hanging over the field for decades. It was one of the main reasons many physicists felt comfortable ignoring the Oppenheimer-Snyder result. If the singularity was just an artifact of idealized symmetry, then it might never occur in the real universe. Penrose demolished that objection in 1965. He published a paper, just a few pages long, that proved a theorem. Not a calculation for a specific case, not a numerical simulation, but a mathematical theorem, a proof that applies universally, regardless of symmetry, regardless of the detailed properties of the collapsing matter. The key concept Penrose introduced was the trapped surface, a closed, two-dimensional surface with the property that all light rays emitted from it, in every direction, converge inward.
In normal space, if you emit light from a sphere, the outward-pointing rays spread out, and the inward-pointing rays converge. But on a trapped surface, even the outward-pointing rays converge. Space is curved so severely that outward isn't really outward anymore. Every direction leads deeper in. Penrose showed that once a trapped surface forms, which requires only that enough mass is concentrated into a small enough region, the formation of a singularity is inevitable. The details of the collapse don't matter. The shape doesn't matter. The composition doesn't matter. The lumps and irregularities and asymmetries that make a real collapse different from the idealized Oppenheimer-Snyder scenario, none of that can save you. Once a trapped surface exists, general relativity guarantees that space-time will develop a singularity somewhere in the future of that surface, and no physical process operating within the framework of general relativity can prevent it.
The proof used a technique called a topological argument, which was new to physics at the time, though well established in mathematics. Penrose wasn't solving equations or computing numbers. He was using the global structure of space-time, the way light cones tip and deform in the presence of extreme curvature, to show that certain outcomes are logically inescapable. It was a proof by contradiction. Assume there is no singularity, show that this leads to a logical impossibility, and conclude that a singularity must form. This was a watershed moment. Penrose's singularity theorem took the question of gravitational collapse out of the realm of special cases and approximations and placed it on solid mathematical ground. Singularities weren't quirks of idealized models. They were built into the fabric of the theory. If general relativity is correct, and all the evidence says it is, then singularities must exist.
Stephen Hawking, then a young graduate student at Cambridge, immediately recognized the importance of Penrose's approach and extended it. Working together and separately through the mid to late 1960s, Penrose and Hawking proved a series of singularity theorems, showing that singularities are not rare or exotic, but generic features of general relativistic spacetimes. Under very broad conditions that appear to be satisfied in the real universe, general relativity predicts singular behavior. The theorems applied not just to collapsing stars, but to the universe as a whole, implying that the Big Bang itself was a singularity, a point of infinite density in the past of our cosmos. For the black hole story, the implication was clear. Real stars, messy, irregular, rotating, lumpy stars, really do collapse to singularities. The objection that had sheltered skeptics for decades was gone.
While Penrose was working on singularity theorems, another piece of the hidden revolution was falling into place. In 1963, a New Zealand mathematician named Roy Kerr found a solution to Einstein's field equations that described something Schwarzschild's original solution didn't: a rotating black hole. And this mattered enormously, because real objects rotate. Every star in the universe spins. When a star collapses, that spin doesn't go away. It gets amplified dramatically by the same principle that makes an ice skater spin faster when they pull their arms in. A slowly rotating star, collapsing down to a fraction of its original size, would produce a rapidly spinning compact remnant. Any black hole formed from a real stellar collapse would be rotating. Schwarzschild's non-rotating solution was a beautiful idealization, a perfectly spherical cow in a vacuum, useful for understanding the basic physics, but not what nature actually produces.
Kerr's rotating solution was the real thing. And the Kerr solution was far more mathematically complex than Schwarzschild's. It had taken nearly 50 years for anyone to find it, and Kerr himself later said that when he presented it at a conference in Texas in 1963, most of the audience didn't immediately grasp its significance. The legendary astrophysicist Achilles Papapetrou reportedly stood up and asked Kerr to repeat the key result, and there was a moment of stunned silence when the implications sank in. The geometry described by Kerr's solution was both beautiful and bizarre. A rotating black hole doesn't just have an event horizon. It has a second boundary outside the horizon called the ergosphere, a region where space-time itself is dragged around by the rotation so forcefully that nothing can stand still. Not even light. Everything in the ergosphere is dragged along in the direction of the black hole's rotation, carried by the current of space-time itself. You could fire your rockets at full power, trying to stay in place, and space-time would still drag you around. The rotation of the black hole literally twists the geometry of the universe around it. And the singularity at the center isn't a point, as in the Schwarzschild case. It's a ring. A ring singularity. The radius of the ring determined by the black hole's spin. The implications are strange and speculative. In the idealized Kerr geometry, the interior of the black hole contains pathways that lead to other regions of space-time, other universes in the maximal mathematical extension of the solution.
Whether any of these mathematical possibilities correspond to physical reality is still debated. But the structure of the solution hinted at a richness that went far beyond anything the simple Schwarzschild picture had suggested. There's a beautiful theorem, proved in the late 1960s and early 70s by Werner Israel, Brandon Carter and others, sometimes called the no-hair theorem. It says that a stationary black hole in general relativity is completely characterized by just three numbers: its mass, its spin, and its electric charge. That's it. Everything else, every detail about what formed the black hole, the composition of the original star, its internal structure, whether it was made of iron or hydrogen or old textbooks, all of that information is irrelevant to the external geometry. The black hole forgets its origins. All the complexity of the collapsing matter is hidden behind the event horizon, and all that remains visible from outside are three numbers. Wheeler summarized this with characteristic flair. Black holes have no hair, meaning they have no distinguishing features beyond those three parameters. A bald, featureless boundary, characterized by mass, spin, and charge, with everything else hidden inside, inaccessible forever. This was both elegant and deeply troubling, because it raised a question that would later become the most important question in all of black hole physics. If the black hole forgets everything about what formed it, where does all that information go? But that question was still a few years from being asked properly. We'll come back to it. But the point for our story is this. By the mid-1960s, the theoretical picture had snapped into focus with extraordinary clarity. Penrose had proved that singularities are inevitable. Kerr had found the solution for rotating black holes. Wheeler had given the objects a name that the whole world could remember. The golden age of black hole physics had begun. And all of this, every theorem, every solution, every breakthrough, happened in the realm of theory. Mathematics on paper, equations and proofs.
The objects themselves remained invisible, hidden, theoretical. Nobody had observed a black hole. Nobody had detected one. Nobody had any direct evidence that they existed in the real universe, as opposed to the imaginary universe of mathematical physics. The visible product of this era was intellectual. Papers, theorems, a name. The hidden question was physical. Are these things actually out there? That question would begin to be answered through X-ray telescopes and tracking stars and listening for space-time vibrations. But before the observers could catch up, the theorists were about to discover something that would turn the entire field upside down. A graduate student was about to walk into his advisor's office and suggest something that sounded insane. That black holes, the blackest objects in the universe, the objects from which nothing can escape, have a temperature, that they glow.
And his advisor, Stephen Hawking, was about to set out to prove him wrong and accidentally prove him right, in a way that would uncover the deepest puzzle in all of physics. Jacob Bekenstein was a graduate student at Princeton in the early 1970s, working under John Wheeler. He was quiet, thoughtful, deeply religious, and possessed of the kind of intellectual stubbornness that drives great discoveries. Bekenstein had been thinking about a question that seemed, at first, like a minor technical puzzle, but would turn out to be a gateway to one of the most profound crises in the history of physics. The question was about entropy. Entropy is one of those concepts that sounds abstract until you understand what it really means, and then it feels like one of the most important ideas in all of science. In the simplest terms, entropy is a measure of disorder, of the number of different microscopic arrangements that could produce the same macroscopic appearance.
A tidy room has low entropy. Everything is in its place, and there aren't many ways to keep it that tidy. A messy room has high entropy. There are millions of ways for things to be scattered around. The second law of thermodynamics says that the total entropy of a closed system never decreases. Things get messier. Disorder increases. Hot coffee cools. Ice melts. Rooms get untidy. Time flows in the direction of increasing entropy. This law is one of the most fundamental and reliable in all of physics. It has never been observed to fail. And Bekenstein noticed a problem. What happens if you take a box full of hot gas, a box with a lot of entropy, and you throw it into a black hole? The gas crosses the event horizon, disappears from the observable universe, and the entropy it carried goes with it. From the perspective of the outside universe, the entropy has vanished. The total entropy of everything you can see and measure has decreased.
And that would violate the second law of thermodynamics. Bekenstein found this deeply troubling. The second law isn't a suggestion, it's a foundation. If black holes could erase entropy, the entire edifice of thermodynamics would develop a crack. There would be a loophole, a way to cheat the most reliable rule in physics. Just toss your entropy into a black hole and watch it disappear. Unless the black hole itself carries entropy. That was Bekenstein's radical idea, published in 1972 and 1973. He proposed that black holes are not thermodynamic blank slates. They have entropy, and that entropy is proportional to the area of the event horizon. Not the volume, the area. The surface area of the horizon. Every time you throw something into a black hole, the mass increases, the horizon grows, and the black hole's entropy increases by at least as much as the entropy of whatever fell in.
The second law is saved, but you have to generalize it. The total entropy of the stuff outside the black hole plus the entropy of the black hole itself never decreases. This was strange and beautiful, and it had an immediate, unsettling consequence that Bekenstein himself understood perfectly well. If a black hole has entropy, then by the standard relationships of thermodynamics, it should also have a temperature. And if it has a temperature, it should radiate energy the way any warm object does. A hot coal glows red. A warm body emits infrared radiation. Anything with a temperature above absolute zero radiates. So if a black hole has a temperature, it should glow. But black holes are black. That's the whole point. Nothing escapes from inside the event horizon. How could a black hole radiate? Many physicists thought Bekenstein had made a mistake, that he was taking a mathematical analogy too literally.
Yes, the equations governing black hole mechanics looked structurally similar to the equations of thermodynamics. Horizon area played the role of entropy. Surface gravity played the role of temperature. But maybe this was just a coincidence, a formal resemblance, not deep physics. Stephen Hawking was among the skeptics. He had himself proved a beautiful theorem in 1971, showing that the total area of event horizons can never decrease. If two black holes merge, the area of the new horizon is always at least as large as the sum of the original two. He noticed the parallel with entropy. The second law of thermodynamics says entropy never decreases, and his area theorem says horizon area never decreases. But Hawking thought Bekenstein was reading too much into the parallel.
Hawking set out to do a careful quantum mechanical calculation near the event horizon, intending to show rigorously that black holes don't radiate, that the thermodynamic analogy was just a coincidence, and that Bekenstein had overreached. He spent months on the calculation, through late 1973 and into 1974. He applied quantum field theory to the curved space-time around a black hole, treating the gravitational field classically using general relativity, while treating the matter fields quantum mechanically. This is a technique called systemal gravity, and it's the best tool available when you don't have a full theory of quantum gravity. And what he found shocked him. It shocked everyone. Black holes do radiate. Let me try to explain how, because this is one of the deepest results in modern physics, and it deserves careful attention. Start with quantum field theory, which tells us that empty space isn't really empty.
Even in a perfect vacuum, far from any matter, quantum fields are fluctuating. There's an irreducible quantum fuzz, a constant shimmering of virtual activity at every point in space. In flat spacetime, with no gravity, no curvature, these fluctuations are invisible to all observers. Everyone agrees that the vacuum is empty. No particles are being created. But near a black hole, spacetime is severely curved. And in curved spacetime, something strange happens. Different observers can disagree about the number of particles that exist. This isn't a matter of opinion or perspective. It's a mathematical consequence of the way quantum fields are defined in curved geometry. The very concept of particle depends on your reference frame. And when spacetime is dramatically warped, different frames lead to genuinely different but equally valid descriptions of the same physics.
What Hawking showed is that an observer far from the black hole, floating safely at a great distance, would detect a faint but steady stream of particles coming from the direction of the event horizon. To that distant observer, the black hole is glowing, very, very faintly. Almost immeasurably faintly, but genuinely, physically glowing. And the spectrum of that radiation, the pattern of wavelengths, is exactly thermal. It's the spectrum of a perfect black body, the same kind of radiation emitted by a hot oven or a warm coal or any object at a well-defined temperature. The black hole has a temperature, just as Bekenstein's entropy calculation implied. And that temperature depends on the mass of the black hole in a beautifully clean way. The temperature is inversely proportional to the mass. Smaller black holes are hotter. Larger black holes are colder. For a black hole with the mass of our Sun, the Hawking temperature is about 60 billionths of a Kelvin. That's not just cold. It's colder than the cosmic microwave background radiation that fills all of space, which sits at about 2.7 Kelvin. A solar mass black hole is absorbing far more energy from the ambient cosmic radiation than it's losing through Hawking radiation. It's gaining mass, not losing it. For any black hole that could actually form from a collapsing star, Hawking radiation is utterly negligible, far too faint to detect, far too weak to matter on any timescale relevant to the current age of the universe. But the principle matters. Because Hawking radiation means that black holes are not eternal. Think about it. The black hole is radiating energy, slowly, unimaginably slowly, but it is losing mass. And as it loses mass, it gets smaller, and as it gets smaller, its temperature goes up. And as its temperature goes up, it radiates faster. And as it radiates faster, it loses mass more quickly.
And as it loses mass more quickly, it gets even smaller and even hotter and radiates even faster. It's a runaway process, an accelerating feedback loop. For most of a black hole's life, nothing much happens. It sits there, faintly glowing at a temperature barely above absolute zero, losing mass at an imperceptible rate. But eventually, given enough time, the mass drops low enough that the process accelerates dramatically. The final moments of a black hole's life would be an explosion, a burst of radiation releasing energy comparable to millions of megatons of nuclear weapons.
as the last remnants of the black hole evaporate in a flash. For a stellar mass black hole, this entire process would take something like 10 to the power of 67 years. That number is so enormous, it defies comprehension. The current age of the universe is about 14 billion years, roughly 10 to the power of 10 years.
We're talking about timescales that exceed the age of the universe by a factor of 10 to the 57th power. So this is not a practical concern for any existing black hole. But the theoretical implication is profound. Given enough time, every black hole will evaporate completely and vanish. Before Hawking, black holes were forever. They were the ultimate endpoints of gravitational collapse. Matter goes in, nothing comes out, the end. After Hawking, black holes became temporary, incredibly long-lived but temporary. They are born from collapsing stars. They exist for timescales that dwarf the age of the universe, and eventually they die. They have a life cycle: birth, existence, death, just like everything else. Hawking published this result in 1974 in the journal Nature, and a more detailed version in 1975. It was immediately recognized as one of the great results in theoretical physics.
It united three previously separate domains: general relativity, quantum mechanics, and thermodynamics. The temperature of a black hole is a formula that contains all three fundamental constants: the speed of light, Planck's constant, and Newton's gravitational constant. It's the only known result that brings all three together in a single equation. It felt, and still feels, like a signpost pointing toward a deeper theory, a theory of quantum gravity that unifies all of physics. But the result also created a problem so deep, so fundamentally challenging, that it has consumed theoretical physics for half a century and still has no universally accepted resolution. That problem is the black hole information paradox. Here's the issue. In quantum mechanics, there's a principle called unitarity. It says, essentially, that information is never destroyed. The total amount of quantum information in a closed system is always conserved.
If you know the exact quantum state of a system at one time, you can, in principle, calculate its state at any other time, past or future. The laws of quantum mechanics are reversible. Nothing is truly lost. But look at what Hawking radiation seems to imply. A black hole forms from the collapse of a star made of specific atoms, with a specific composition, a specific history. All of that detailed information falls past the event horizon and becomes inaccessible. Then the black hole evaporates, slowly, through Hawking radiation. And Hawking showed that the radiation is thermal, purely thermal, characterized only by the black hole's temperature. A thermal spectrum contains no information about what formed the black hole. It's the same whether the black hole was made from a collapsing star, a pile of books, or a billion elephants. The radiation carries no fingerprint of the original matter. So where does the information go?
The original star had a specific, detailed quantum state. The radiation at the end is generic, featureless, thermal. If the black hole evaporates completely, leaving nothing behind but this featureless radiation, then the detailed information about the original star has been irreversibly destroyed. Quantum information has been lost, and that violates unitarity, one of the most sacred principles of quantum mechanics. This is the information paradox. It's not a minor technical puzzle. It's a head-on collision between the two pillars of modern physics: general relativity, which predicts black holes and event horizons, and quantum mechanics, which insists that information can never be destroyed. They can't both be completely right, at least not in their current forms, Something has to give. Hawking himself took a clear position. Information is genuinely lost. Quantum mechanics, he argued, needs to be modified in the presence of strong gravity. The formation and evaporation of a black hole is a process that converts pure quantum states into mixed thermal states, destroying information in the process. He called this non-unitary evolution, and he maintained this position for 30 years. Most other physicists disagreed, led primarily by Leonard Susskind at Stanford and Gerard 't Hooft in the Netherlands. The majority view was that information must somehow be preserved, that unitarity is too fundamental to be violated, and that the paradox reflects our incomplete understanding of quantum gravity rather than a genuine failure of quantum mechanics. Susskind, in particular, fought this battle with enormous tenacity and creativity over decades. He has described his motivation in personal terms. If Hawking was right and information could be destroyed, then it wouldn't just be a technical problem in theoretical physics. It would mean that the most fundamental principle of quantum mechanics, the one that guarantees the consistency and predictability of the theory, would be broken. Everything downstream of quantum mechanics, chemistry, molecular biology, the reliability of computation, the coherence of the physical world, all of it rests on the assumption that quantum evolution is unitary, that the laws of physics are fundamentally reversible, that information is conserved. Susskind felt that giving up unitarity was giving up too much. He developed the idea of black hole complementarity, a proposal that attempted to resolve the paradox by taking both the external and internal perspectives seriously, but declaring them complementary in the quantum mechanical sense. The idea was that the experience of an observer falling through the horizon and the description constructed by an observer watching from outside are both valid, but they can never be directly compared. No single observer can see both descriptions simultaneously. The falling observer crosses a smooth, uneventful horizon and plunges toward the singularity. The external observer sees the information gradually scrambled and re-radiated in the Hawking radiation. Both descriptions are self-consistent. The contradiction only arises if you try to paste them together into a single picture, and complementarity says you're not allowed to do that. The idea was controversial. In 2012, a team of physicists, including Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, known collectively by their initials as AMPS, published a paper arguing that black hole complementarity leads to a paradox of its own. They showed that you can't simultaneously have a smooth horizon, unitarity, and the validity of quantum field theory at low energies. At least one has to give. Their proposed resolution was dramatic. The event horizon might not be smooth at all. It might be a firewall, a searing barrier of high-energy particles that would incinerate anything crossing it. This would save unitarity, but destroy the smoothness of the horizon, one of the most basic predictions of general relativity. The firewall proposal shocked the field and generated intense debate. Most physicists found it difficult to accept, because general relativity so clearly predicts a smooth horizon, and because the equivalence principle, the foundational idea that got Einstein started in the first place, demands that a freely falling observer notice nothing special at the horizon. The debate remains unresolved. Firewalls, fuzzballs, soft hair, island formulas. A whole ecosystem of proposed solutions has emerged, each with its own virtues and its own problems. The debate between Hawking and Susskind became one of the great intellectual battles of modern physics.
They respected each other, but they fundamentally disagreed about the nature of reality at its deepest level. Hawking was willing to sacrifice quantum mechanics. Susskind was willing to sacrifice our intuitive understanding of space-time. The stakes could not have been higher. The resolution of this paradox would determine whether quantum mechanics or general relativity is more fundamental, and it would provide the strongest clues yet about what a theory of quantum gravity might look like.
In 1997, a young theorist named Juan Maldacena, working at Harvard, published a paper that changed the landscape entirely. Maldacena was born in Argentina and had done his graduate work at Princeton. He was 30 years old when he published what may be the most influential paper in theoretical physics of the past 3 decades. As of today, it has been cited over 20,000 times, making it one of the most cited papers in the history of physics.
What Maldacena proposed was a conjecture now known as the ADS/CFT correspondence, or gauge/gravity duality. The idea, stated as simply as I can manage, is this: a theory of quantum gravity in a specific kind of space-time, called anti-de Sitter space, is exactly mathematically equivalent to a quantum field theory living on the boundary of that space-time. Anti-de Sitter space has a negative cosmological constant, which means it has a natural boundary at spatial infinity, a kind of container wall. And Maldacena showed that everything happening in the bulk, the interior of this space-time, including all the complicated gravitational dynamics, black holes, curved geometry, singularities, all of it, can be fully described by a quantum theory living on the boundary, a theory that has no gravity at all. This is the holographic principle made mathematically precise.
The three-dimensional interior, with all its gravitational complexity, is a kind of hologram projected from the two-dimensional boundary. And here's the key point for the information paradox. The quantum field theory on the boundary is a perfectly ordinary, well-understood type of quantum theory. And it's unitary. Information is conserved in the boundary theory. There are no exceptions, no loopholes. If the boundary theory is unitary, then the bulk theory must be too, because they're the same theory, just described in different languages. In the world described by ADS/CFT, information cannot be lost in a black hole. The formation and evaporation of a black hole in the bulk corresponds to some complicated but perfectly unitary process in the boundary theory. Information goes in, gets scrambled, and eventually comes back out. Nothing is lost. This was not a rigorous proof that information is preserved in our universe. Our universe doesn't appear to be anti-de Sitter space. It has a positive cosmological constant, more like de Sitter space, and extending Maldacena's result to realistic cosmologies remains an open problem. But ADS/CFT was so mathematically powerful, so internally consistent, and so rich in consequences that it tilted the field decisively toward the view that information is preserved. Hawking himself eventually conceded in 2004 at a conference in Dublin. The announcement was treated as major news. Hawking, who by this point communicated through a speech synthesizer and could compose only a few words per minute, had prepared a formal statement. He said that he had been wrong, that information is not lost in black hole evaporation, and that the paradox could be resolved within the framework of quantum mechanics as it stands. He paid off a bet he'd made with John Preskill of Caltech in 1997, presenting Preskill with an encyclopedia of baseball, from which information can, in principle, be recovered. Preskill accepted the encyclopedia, but later admitted that he wasn't entirely sure what Hawking's argument was, and that the concession seemed to come more from a change in Hawking's intuition than from a rigorous proof. Susskind, who had also been on the losing end of a bet with Hawking, was more satisfied. He felt vindicated, though he acknowledged that the battle had been productive for everyone involved, forcing both sides to develop ideas and techniques that might never have emerged otherwise. The concession, while symbolically important, didn't resolve the paradox. Saying that information is preserved is the easy part. Explaining how it gets out, through what mechanism the detailed quantum information about everything that fell into the black hole is encoded in the Hawking radiation, that's the hard part. And that question remains one of the deepest open problems in all of physics. In recent years, there has been remarkable progress. Calculations involving quantum extremal surfaces and contributions from space-time geometries, called replica wormholes, have shown that, at least in certain theoretical settings, the gravitational theory itself is consistent with unitarity. The entropy of the Hawking radiation follows a specific pattern, first increasing and then decreasing, called the Page curve, after the physicist Don Page, who proposed it in 1993. Reproducing the Page curve from a gravitational calculation was a genuine breakthrough, achieved in 2019 by several groups, including work by Jeff Pennington and by Ahmed Almheiri, Nima Arkani Hamed, Daniel Harlow, and others. But these results come with caveats. They work cleanly within the ADS/CFT framework, in a space-time that isn't the one we live in. Extending them to our universe, with its positive cosmological constant and its lack of a convenient boundary, is an unsolved problem. And even within ADS/CFT, the detailed mechanism by which information escapes the black hole remains elusive. We know the entropy follows the right curve. We don't yet have a blow-by-blow account of how the information gets encoded in the outgoing radiation. So the paradox persists, evolved but unresolved.
The visible product of 50 years of work. The Hawking radiation formula, the entropy formula, the Page curve calculations. These are among the most beautiful results in theoretical physics. The hidden core, the actual mechanism of information recovery, the true nature of the black hole interior, what replaces the singularity when quantum gravity is properly accounted for. All of that remains in the dark. The brightest minds in physics have been staring at this darkness for half a century, and the darkness hasn't blinked yet. But the theorists weren't the only ones who were making progress. While Hawking and Susskind and Maldacena were arguing about information and entropy and the nature of space-time, something equally extraordinary was happening on the observational side of physics. People were building instruments, not to study the hidden interior of a black hole, which may be forever beyond our reach, but to detect the visible signatures, the fingerprints that black holes leave on the universe around them. Signatures in X-rays, in starlight, in the very ripples of space-time itself. And what they found would transform black holes from theoretical constructs into observed astrophysical realities, as concrete and undeniable as the stars themselves. For decades after Oppenheimer and Snyder's paper, black holes were creatures of theory. They lived in equations, in proofs, in the arguments of physicists. But they had never been observed. No one had seen one. No one had detected one. And while the theoretical case was growing stronger with every passing year, Penrose's theorems, Kerr's solution, Wheeler's championship, there remained a perfectly reasonable position that said, until we see evidence, these remain mathematical possibilities, not physical realities. General relativity might be correct in principle, but incomplete in practice. Maybe some unknown mechanism really does prevent full collapse in nature, even if we can't identify it in the equations. Absence of a known mechanism isn't proof that no mechanism exists. The observational hunt for black holes required a new way of seeing the universe. Visible light, the narrow band of electromagnetic radiation that human eyes can detect, isn't enough. Black holes don't emit visible light, and the processes happening near them often radiate most of their energy at wavelengths human eyes can't see. X-rays, radio waves, gamma rays. To find black holes, astronomers needed to extend their vision beyond the visible spectrum, and that meant getting above the atmosphere. The observational hunt started, oddly enough, with a bang. The birth of X-ray astronomy. On June 18, 1962, a small Aerobee sounding rocket launched from White Sands, New Mexico, carrying a set of Geiger counters designed to detect X-rays from the moon. The experiment was led by Riccardo Giacconi, an Italian-American physicist
who would later win the Nobel Prize for this work. The Moon turned out to be a boring X-ray source. But the detectors picked up something far more interesting. A brilliant X-ray source in the constellation Scorpius, the first extraterrestrial X-ray source ever detected, which they named Scorpius X1. This was a surprise. The Sun emits X-rays, but weakly. Nobody expected the sky to be full of bright X-ray sources, and the X-rays couldn't be observed from the ground because Earth's atmosphere absorbs them. You needed to get above the atmosphere. You needed rockets and eventually satellites. On December 12, 1970, NASA launched Uhuru, the first satellite dedicated entirely to X-ray astronomy. It was launched from a platform off the coast of Kenya, and the name Uhuru is Swahili for freedom, because the launch coincided with Kenya's Independence Day. Uhuru catalogued over 300 X-ray sources across the sky, and among them was one that would become the first widely accepted black hole candidate, Cygnus X1. Cygnus X1 had actually been detected before Uhuru during earlier rocket flights in 1964, but Uhuru's observations revealed something crucial. The X-ray emission was flickering. It was varying on timescales of fractions of a second, sometimes milliseconds. And this tells you something profound about the size of the source. If a light source flickers coherently, meaning the brightness changes all at once rather than in patches, the emitting region can't be bigger than the distance light can travel during the flickering time. Millisecond flickering means the emitting region is at most a couple hundred miles across. A couple hundred miles, pouring out energy thousands of times the total output of the Sun, mostly in X-rays. Whatever was producing this had to be extraordinarily compact and extraordinarily energetic. Meanwhile, optical telescopes pointed at the same patch of sky and found a visible companion, a blue supergiant star called HDE 226868. And by studying the Doppler shifts in the light from that star, watching its spectral lines wobble back and forth as it orbited, astronomers could tell it was dancing around an invisible partner. The orbital mechanics gave an estimate of the invisible companion's mass, more than 10 times the mass of the Sun, far too massive to be a neutron star, which has an upper limit of about 2 to 3 solar masses, too massive for a neutron star, too compact for any known alternative. The conclusion? Cautiously at first, then with growing confidence, the invisible companion in the Cygnus X1 system was a black hole. And here's a detail I love. In 1974, Stephen Hawking made a bet with Kip Thorne that Cygnus X1 was not a black hole. Hawking later described it as an insurance policy. If black holes turned out not to exist, at least he'd win the bet and get a subscription to Private Eye magazine. If Thorne won, Hawking owed him a subscription to Penthouse. By 1990, the evidence was overwhelming, and Hawking conceded, reportedly sneaking into Thorne's office while Thorne was away and signing the concession. His wife at the time was apparently not delighted about the specific terms of the wager. The playful bet masked a serious point. By the 90s, the evidence for stellar mass black holes, the kind formed from collapsing stars, was becoming airtight. Cygnus X1 was just the first. Astronomers found more X-ray binaries with invisible companions too massive to be neutron stars, LMC X3, A0620-00, V404 Cygni. Each one told the same story. A visible star orbiting something dark, something compact, something heavy, with X-rays blazing from the infalling gas. But stellar mass black holes, weighing in at maybe 5 to 50 times the mass of the Sun, were only one part of the story. There was another kind, far larger, far more powerful, lurking in the centers of galaxies. Supermassive black holes, millions to billions of solar masses, and the evidence for those was about to become spectacular. The quasars that had so baffled astronomers in the 1960s, those impossibly bright, point-like sources at enormous distances, turned out to be powered by supermassive black holes actively devouring gas. Matter spiraling into a supermassive black hole forms an accretion disk, heated to millions of degrees, shining with the luminosity of entire galaxies. A quasar is a supermassive black hole at dinner time, and the energy released by the meal outshines everything else in the vicinity by orders of magnitude. But you don't need an active quasar to find a supermassive black hole. Most galaxies harbor one at their center, including our own Milky Way. And the evidence for the one at the center of our galaxy is some of the most beautiful observational work in the history of science. The source is called Sagittarius A star, and it sits about 26,000 light-years from us in the dense, dusty heart of the galaxy. You can't see it in visible light because the dust blocks the view, but you can observe it in radio waves and infrared. In the 1990s, two teams independently began a project that would span decades. One was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, using telescopes in Chile. The other was led by Andrea Ghez at UCLA, using the Keck telescopes in Hawaii. Both teams set out to do something that required extraordinary patience and precision. Track the motions of individual stars orbiting close to the galactic center. Year after year, decade after decade, building up their orbital paths, point by point. Think about what that requires. You're measuring the positions of stars 26,000 light-years away, with enough precision to track their orbits. You need adaptive optics, a technique that corrects for the blurring of Earth's atmosphere in real time. Using lasers to create artificial guide stars high in the atmosphere. You need years and decades of observations, because the orbital periods of these stars range from about 16 years for the closest known one, called S2, to much longer for stars farther out. Over the years, Genzel and Ghez built up a stunning dataset. They watched S2 complete a full orbit around the invisible center, whipping around at speeds exceeding 4,300 miles per second at its closest approach, about 2.5% the speed of light. At its nearest point to the center, S2 comes within about 120 astronomical units, roughly 4 times the distance from the Sun to Neptune. That's close enough that general relativistic effects become measurable. In 2018, both teams independently detected the gravitational redshift of S2's light as the star swung past the central mass at its closest approach, a prediction of general relativity that had never been tested in such a strong gravitational field around such a massive object. The light from S2 was noticeably shifted toward the red end of the spectrum, stretched by the gravity of whatever it was orbiting, exactly as Einstein's equations predicted. A year later, in 2019, the Genzel team detected another effect, the precession of S2's orbit. In Newtonian gravity, an orbit around a spherical mass would trace out a perfect, unchanging ellipse. In general relativity, the ellipse itself rotates, slowly turning around the central mass. This Schwarzschild precession, as it's called, is the same effect that explained the anomaly in Mercury's orbit that Newton couldn't account for. The very anomaly that helped confirm general relativity in the first place. But now it was being measured around an object 4 million times the mass of the Sun, in a gravitational field incomparably stronger than the Sun's. And the precession matched Einstein's predictions precisely. From the orbit of S2 and other stars, both teams calculated the mass of the invisible object they were all orbiting, about 4 million solar masses, crammed into a region smaller than our solar system, 4 million times the mass of our Sun, confined to a space you could fit between the Sun and the orbit of Mercury. There is nothing in known physics other than a black hole that can pack that much mass into that smaller volume. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this work, alongside Roger Penrose for his singularity theorem. The theorist who proved that black holes must form, and the observers who proved that they have formed. And then came the photographs. The Event Horizon Telescope project, led by Shepard Dolman, aimed to do something that sounded impossible: image the shadow of a black hole directly. The problem was resolution. Black holes are small for their mass. The event horizon of Sagittarius A star, despite its 4 million solar masses, subtends an angle on the sky of roughly 50 micro-arcseconds. That's like trying to read the date on a coin in Los Angeles while standing in New York. No single telescope on Earth can resolve that.
But you don't need a single dish. A technique called very long baseline interferometry allows you to combine radio telescopes separated by large distances and achieve the angular resolution corresponding to a telescope as wide as the distance between them. If your dishes are on opposite sides of the Earth, your resolution corresponds to an Earth-sized telescope. The EHT assembled 8 telescope sites on 6 continents, including the South Pole, the Atacama Desert in Chile at about 16,000 feet elevation, telescopes in Hawaii, Arizona, Spain, Mexico, and France. Each site was equipped with identical receivers, hydrogen maser atomic clocks, precise to a trillionth of a second, and banks of hard drives recording data at staggering rates. The data, about 5 petabytes of it, half a ton of hard drives, was physically shipped to processing centers at MIT and the Max Planck Institute in Bonn, because no internet connection was fast enough to transfer it.
In April 2017, all 8 sites simultaneously observed 2 targets, Sagittarius A star at the center of our galaxy and M87 star, the supermassive black hole at the heart of the giant elliptical galaxy Messier 87, about 55 million light-years away. M87 star is far more distant than Sagittarius A star, but about 1,500 times more massive, 6.5 billion solar masses, so its shadow appears roughly the same angular size on the sky. And because it's so much more massive, the timescale on which the swirling gas around it changes is much longer, hours rather than minutes, making it a steadier target. 2 years of processing followed, and those 2 years tell their own story about the boundary between seeing and understanding. The raw data, 5 petabytes of it, recorded on half a ton of hard drives, was shipped physically to correlator centers at MIT Haystack and the Max Planck Institute for Radio Astronomy in Bonn. The correlation process was painstaking, lining up signals recorded at stations thousands of miles apart. Signals that had passed through different patches of turbulent atmosphere, aligning them to sub-wavelength precision. The teams developed 4 completely separate imaging algorithms to reconstruct images from the interferometric data, because if the image depended on which algorithm you used, you couldn't trust it. They generated fake data from computer simulations, scrambled it, and checked whether their pipelines could recover the known input. They tested themselves against their own artificial challenges before they dared look at the real result. They were painstaking, almost agonizingly careful, because they understood what was at stake. Katie Bauman, then a postdoctoral researcher who had helped develop one of the key imaging algorithms while still a graduate student at MIT, later described the moment with visible emotion. A now famous photograph captured her staring at her laptop screen as the image materialized, hands clasped in front of her face. The team ran the 4 independent pipelines and compared the outputs. All 4 produced essentially the same image, an asymmetric ring, bright on one side, surrounding a dark center. the convergence between independent algorithms was the strongest evidence that the image was real, that they had actually photographed something and not generated an artifact. And then, on April 10th, 2019, the image we started with tonight was released at 6 simultaneous press conferences around the world. The asymmetric ring of glowing plasma, bright on one side where the gas is moving toward us, Doppler boosted and brightened, dimmer on the other side where it's moving away, and at the center, the dark shadow, the absence, the region from which no photons can escape to reach our telescopes.
The size of the shadow matched the prediction for a 6.5 billion solar mass black hole. General relativity, tested at the edge of an event horizon, passed with extraordinary precision. 3 years later, in May 2022, the EHT collaboration released an image of Sagittarius A star as well, our own galaxy's black hole. Harder to image because the gas dynamics change on minute-by-minute timescales, requiring more sophisticated processing. But there it was, another ring of light, another dark shadow, another silent confirmation that the objects Schwarzschild's mathematics had predicted over a century ago actually exist. But between the M87 star image and the Sagittarius A star image, something else happened that was equally momentous, though it came through an entirely different channel of observation.
On September 14th, 2015, at 5:51 in the morning Eastern Time, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, simultaneously registered a signal. Let me tell you a bit about how LIGO works, because the sheer audacity of the engineering deserves attention. Each LIGO detector is an L-shaped vacuum system with 2 arms, each about 2.5 miles long. A laser beam is split in 2, sent down both arms, bounced off mirrors at the far ends, and recombined. If both arms are exactly the same length, the 2 returning beams cancel each other out through destructive interference. Silence. But if a gravitational wave passes through, it stretches space along one arm and compresses it along the other, changing the relative lengths by an incredibly tiny amount. The beams no longer cancel perfectly. A faint signal appears. How tiny is the change in length that LIGO can detect? About 1,000th the diameter of a proton.
That's not a typo. The mirrors are 2.5 miles apart, and LIGO can detect a change in that distance of about 10 to the minus 19 meters. To put that in perspective, if LIGO's arm were the distance from the Sun to the nearest star, about 4 light-years, a gravitational wave detection would correspond to a change in that distance of about the width of a human hair. The precision required is almost absurd. Seismic vibrations from traffic, ocean waves, even someone walking near the building, all of these produce disturbances millions of times larger than the signal LIGO is looking for. Isolating the mirrors from these disturbances required decades of engineering development. Multi-stage pendulum suspensions, active seismic isolation, vacuum systems, and extraordinary control of every possible source of noise. There are 2 LIGO detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 1,900 miles. A real gravitational wave will arrive at both detectors within a specific time window, the time it takes light to travel between them, about 10 milliseconds. A local disturbance, a truck driving past one site, an earthquake, equipment noise, will appear in only one detector. Having 2 detectors is what allows you to distinguish real signals from noise. And on September 14th, 2015, both detectors registered the same signal within 7 milliseconds of each other. A chirp. A rising and falling wave of gravitational radiation,
space-time itself vibrating. The signal carried the signature of an event that had occurred 1.3 billion years earlier, when multicellular life on Earth was still a relatively recent innovation. Two black holes, one 36 solar masses and one 29 solar masses, had been orbiting each other, spiraling slowly inward over millions of years, losing energy to gravitational radiation.
In their final moments, the orbit tightened dramatically. The two black holes whipped around each other hundreds of times per second, moving at a significant fraction of the speed of light, carving deep furrows in the geometry of space-time. And then they merged, fusing into a single black hole of 62 solar masses. Notice that number. 36 plus 29 is 65. But the final black hole was only 62 solar masses. 3 solar masses were missing. Where did they go? They were radiated away as gravitational waves, as pure energy carried off in the rippling of space-time itself. 3 times the mass of our Sun, converted entirely into gravitational wave energy in a fraction of a second. For that brief instant, the merger radiated more power than all the stars in the observable universe combined. It was the most powerful event ever directly detected by human instruments, and the ripples from that cataclysm, spreading outward at the speed of light, growing weaker and weaker as they crossed the void, traveled for 1.3 billion years. They passed through galaxies, through intergalactic voids, through dust clouds and stellar nurseries, and the empty vastness between galaxy clusters. Until, 1.3 billion years after the merger, a tiny fragment of those ripples reached the Earth and stretched the distance between 2 mirrors in a 2.5-mile vacuum chamber by less than 1,000th the diameter of a proton. And LIGO felt it. The detection was announced in February 2016, and Rainer Weiss, Kip Thorne, and Barry Barish received the Nobel Prize in Physics in 2017 for their roles in making it happen. The prize recognized both the detection and the decades of work that led to it, because LIGO was not a sudden inspiration. It was the product of nearly 50 years of development. Weiss had first sketched the concept in the early 1970s. The project had survived skepticism, funding crises, technical setbacks, and a near-death experience when the initial LIGO detectors, operational from 2002 to 2010, failed to detect any gravitational waves at all. The advanced LIGO upgrade, with dramatically improved sensitivity, made the detection within days of switching on, a coincidence so fortunate that some of the team initially suspected it was a test injection rather than a real signal. Since that first detection, LIGO and its sister detector Virgo in Italy have recorded dozens of black hole mergers, along with neutron star collisions and mixed events where a black hole and a neutron star spiral together. Each detection provides precise measurements of the merging object's masses, spins, and distances. Each one tests general relativity in the strong field regime, where gravity is most extreme. And so far, Einstein's theory has passed every test. So here we are. Black holes are no longer theoretical objects. They are observed realities. We have photographed them. We have listened to them collide. We have tracked stars orbiting them for decades. The visible evidence is overwhelming and convergent. Multiple independent lines of observation, electromagnetic and gravitational, all pointing to the same conclusion. Black holes exist, and they behave exactly as general relativity predicts. But the hidden interior remains completely inaccessible. The event horizon is, by definition, a one-way door. No information from inside can reach us. The singularity, the point of infinite density at the center, the place where our equations break down, is as hidden as it has ever been. We can see the shadow, we can hear the collisions, we can weigh the objects and measure their spins, but we cannot see inside. The deepest truth about black holes. What actually happens at the center? What replaces the singularity when quantum gravity is properly accounted for? Whether information truly escapes or is somehow preserved in a form we don't yet understand. All of that remains in the dark. The visible evidence tells us black holes are real. The hidden questions tell us that our understanding of reality is incomplete. And somehow, both of those facts are deeply thrilling. Let me tell you what's coming next, because the next few decades in black hole science look genuinely extraordinary. The tools being built right now are designed to push directly into the territory where general relativity and quantum mechanics overlap. That contested borderland where our two greatest theories of nature refuse to agree. And for the first time, the instruments might actually be precise enough to see which theory blinks first.
LISA, the Laser Interferometer Space Antenna, is probably the most ambitious thing on the horizon. It's a European Space Agency mission with NASA involvement, and the concept is almost absurdly grand. 3 spacecraft flying in a triangular formation, separated by about 1.5 million miles. That distance, that baseline, is more than 6 times the distance from the Earth to the Moon, and the 3 spacecraft will be connected by laser beams, measuring the tiny changes in distance between them caused by passing gravitational waves. LIGO's arms are 2.5 miles long. LISA's will be about 1.5 million miles. That difference in scale means LISA will be sensitive to gravitational waves at much lower frequencies than LIGO can detect, which means it will hear completely different sources. And the sources LISA is tuned for are exactly the ones that matter most for the deepest questions we've been exploring tonight. Supermassive black hole mergers. When 2 galaxies collide and their central black holes eventually spiral together and merge, that event produces gravitational waves right in LISA's sweet spot. These won't be subtle signals. A supermassive merger could be detectable across most of the observable universe with such high signal quality that the details of the merging process, the ringing of the newly formed black hole as it settles into its final shape, can be measured with extraordinary precision. If general relativity's predictions for the near-horizon geometry are even slightly wrong, if quantum effects leave any imprint at all on those ringing modes, LISA has a real shot at seeing it. There's another class of source that LISA will detect, and this one gets theorists particularly excited: extreme mass ratio inspirals. Imagine a stellar mass black hole, maybe 10 or 20 solar masses, slowly spiraling into a supermassive black hole at the center of a galaxy.
The small object orbits the large one, thousands and thousands of times, before finally plunging in. Each orbit traces out the geometry of space-time near the supermassive black hole with incredible fidelity, like running your fingers over a sculpture in the dark. The gravitational wave signal encodes the shape of space-time near the event horizon. By matching that signal against theoretical predictions, you can test whether the central object really is the black hole that general relativity describes, or something else, something with quantum corrections, something with structure at the horizon, something nobody has predicted yet. The information paradox, the firewall debate, the fuzzball proposal. All of these theoretical arguments ultimately come down to a question about what's happening right at the event horizon. Is it truly featureless, the way classical general relativity describes it?
Or is there some kind of quantum structure, some encoding surface, some physical mechanism that preserves information. For decades, this was a question only theorists could argue about, because no observation could probe the horizon closely enough to distinguish between the possibilities. Extreme mass ratio inspirals are the horizon mappers, and LISA will detect them. The Event Horizon Telescope is evolving too. The next generation EHT aims to roughly double the number of dishes in the array, add stations at new locations around the globe, and push to higher observing frequencies. The goal is sharper images and eventually movies, real-time movies of hot gas swirling around a black hole. Because Sagittarius A star is relatively small as supermassive black holes go, the orbital timescales are short enough that things change on the scale of minutes.
With enough telescopes observing simultaneously, you could watch material orbiting the black hole, see bright spots move, track the dynamics of the accretion flow in something close to real time. Why does a movie matter? Because the way gas moves near the horizon is sensitive to the space-time geometry. The orbital dynamics of hotspots, the timing of flares, the pattern of variability. All of this is predicted by general relativity, and deviations from those predictions could signal new physics. It's another way of probing the same questions, using light instead of gravitational waves. And when you can cross-check results from two fundamentally different kinds of observation, electromagnetic and gravitational, your confidence in whatever you find goes up dramatically. And there's something else. The James Webb Space Telescope is already finding supermassive black holes at surprisingly high redshifts, meaning they existed when the universe was very young.
Black holes that seem too massive, too early. They challenge our models of how supermassive black holes formed and grew. Did they start from the collapse of enormous primordial gas clouds, so-called direct collapse black holes, skipping the stellar stage entirely? Did they grow by merging with each other, galaxy collision after galaxy collision, their central black holes spiraling together? Did some exotic process in the very early universe, in the first fractions of a second after the Big Bang, seed them with primordial black holes formed from density fluctuations? We don't know yet. But the observations are piling up, and they're pushing our models to their limits. Every new detection at high redshift is a data point that constrains the possible formation channels, that narrows the range of allowed histories, that brings us closer to understanding how the seeds of these cosmic monsters were planted.
And all of this, the instruments, the observations, the increasingly precise tests of general relativity, is happening alongside a theoretical revolution that may be even more profound. Remember the information paradox, the collision between general relativity and quantum mechanics, the argument about whether information is lost when a black hole evaporates. That debate has led, over the past 3 decades, to insights that go far beyond black holes themselves. It has led to a growing suspicion among many theoretical physicists that space-time itself, the arena in which we think everything happens, is not fundamental. The idea goes like this. The Bekenstein-Hawking entropy formula tells us that the entropy of a black hole, the amount of information it contains, is proportional to the area of its event horizon, not its volume, its area. This is deeply strange. In ordinary physics, the information content of a region scales with its volume. A bigger box can hold more books.
But for a black hole, the information scales with the surface area of the boundary. It's as if all the information about the 3-dimensional interior is somehow encoded on the 2-dimensional surface. This observation, first articulated by Gerard 't Hooft and then developed extensively by Leonard Susskind, led to the holographic principle, the idea that the information content of any region of space can be fully described by data on the boundary of that region. The 3-dimensional world you experience might be, in some deep sense, a projection from a 2-dimensional surface. The volume is not more fundamental than the boundary. The boundary is the reality. The volume is the projection. In 1997, Maldasena's ADS/CFT correspondence gave the holographic principle a precise mathematical realization, at least for spacetimes with a negative cosmological constant.
In that framework, a theory of quantum gravity in the bulk of the spacetime is exactly equivalent to a quantum field theory living on the boundary. Every question about gravity, about black holes, about the structure of spacetime can be rephrased as a question about a perfectly well-defined quantum system on a lower dimensional surface. And that quantum system is unitary. Information is conserved. Since Maldacena, the field has moved even further. The Ryu-Taklianagi formula, proposed in 2006, showed that the amount of entanglement between two regions of the boundary theory is related to the area of a specific surface in the bulk gravitational theory. Entanglement entropy in the quantum system corresponds to geometric area in the gravitational system. This means that the geometry of spacetime, the distances and curves and surfaces that make up the gravitational universe, is somehow built from entanglement.
The fabric of space itself might be woven from quantum correlations. Mark van Ramsdonk, a physicist at the University of British Columbia, put it vividly in a paper in 2010. He showed that if you gradually reduce the entanglement between two halves of a quantum system, the corresponding spacetime geometry develops a longer and longer bridge between them, stretching like taffy, until eventually, when the entanglement reaches zero, the spacetime splits in two. Disconnect the entanglement, and you disconnect the space. Entanglement is the glue that holds spacetime together. This is an extraordinary claim, and it should be understood for what it is, a result derived within the ADS/CFT framework, which is a specific mathematical setting, not a direct description of our universe. But the result is so clean, so natural, and so deeply connected to other developments in the field that many theorists believe it points towards something universal.
The idea that space is emergent, that it arises from entanglement, has become one of the most active and exciting research programs in theoretical physics, and it connects to other ideas. Leonard Susskind and others have proposed that the computational complexity of a quantum system, how many basic operations are needed to construct a given quantum state from a simple starting state, might be related to the volume behind the event horizon of a black hole. Space behind the horizon keeps growing for an enormous time, and Susskind suggests that this growth corresponds to the growth of quantum complexity in the boundary theory. If true, it means that a concept from computer science, computational complexity, is geometrized by gravity. The inside of a black hole is, in some deep sense, a physical manifestation of how complicated a quantum computation has become. Space isn't just made of entanglement, it's made of computation. Think about what that implies. The distance between 2 points in space, the most basic geometric concept there is, the thing you measure with a ruler, might emerge from the pattern of quantum correlations between microscopic degrees of freedom. When things are highly entangled, they're close together in the emergent geometry. When entanglement is disrupted, space can tear apart. Space isn't the stage on which physics happens. Space is a consequence of the physics. And black holes, in this picture, are the places where this deep structure is most clearly visible. The event horizon is a surface where the entanglement structure of spacetime is organized in a very particular way. The Bekenstein-Hawking entropy is the entanglement entropy between the interior and the exterior. Hawking radiation is the gradual transfer of entanglement from inside-outside correlations to early-late radiation correlations. The information paradox isn't just a puzzle about black holes.
It's a window into the construction manual of reality itself. And there's something else worth knowing about, because it connects the theoretical and observational strands in an unexpected way. Remember Hawking radiation? The prediction that black holes glow faintly due to quantum effects near the horizon. For any real black hole formed from a collapsed star, this radiation is unimaginably faint. A solar mass black hole would have a Hawking temperature of about 60 billionths of a Kelvin, colder than the cosmic microwave background by a factor of about 50 million. Detecting it directly from an astrophysical black hole is beyond any technology we can currently imagine. But physicists have found a creative workaround: analog black holes. These are systems in the laboratory that mimic the essential physics of an event horizon, using completely different physical media. The most elegant version uses sound waves in flowing fluids.
If you set up a fluid flow where the speed of the flow exceeds the local speed of sound, then sound waves in the supersonic region can't travel upstream. They're trapped, carried along by the flow, unable to escape. Exactly the way light is trapped inside a black hole's event horizon. The boundary, where the flow speed equals the sound speed, is an acoustic horizon, and it's mathematically analogous to a gravitational horizon in all the ways that matter for Hawking's calculation. In 2019, Jeff Steinhauer at the Technion in Israel published results from an experiment using a Bose-Einstein condensate, an ultra-cold quantum fluid cooled to just above absolute zero. He created an acoustic horizon in this fluid and detected thermal radiation coming from it. Radiation with a temperature that matched the analog of Hawking's prediction. This wasn't Hawking radiation from a real black hole. The physics was analogous, not identical. But it confirmed that the basic mechanism Hawking identified, the way a horizon interacts with quantum vacuum fluctuations to produce thermal radiation, is real. It works. The mathematics that Hawking developed in 1974 describes something that actually happens in nature, or at least in carefully controlled laboratory analogues of it. And that gives physicists considerably more confidence that real black holes really do radiate, really do slowly evaporate, and that the information paradox is a genuine problem that demands a genuine solution, not just a theoretical curiosity that might go away when we understand the physics better. None of this is settled. These are ideas, frameworks, proposals backed by powerful mathematics, but not yet confirmed by direct astronomical observation.
Extending the holographic principle from ante-de sitter space to the kind of universe we actually live in, a universe with a positive cosmological constant and no convenient boundary, remains one of the biggest open problems in theoretical physics. We still don't have a complete experimentally tested theory of quantum gravity, the singularity at the center of a black hole, the place where the curvature of space-time becomes infinite and our equations stop making sense, is still a mystery. Most physicists believe the singularity is a signal that general relativity is incomplete, that some quantum gravitational theory will resolve it into something finite and comprehensible. Maybe space-time has a discrete structure at the Planck scale, like pixels in a photograph, and you can't squeeze matter into a space smaller than 1 pixel. Maybe the singularity bounces, and the interior of a black hole connects to a new region of space-time, a baby universe budding off from ours. These are real proposals that serious physicists work on. None of them are confirmed. The interior of a black hole is, almost by definition, the hardest place in the universe to get information from. Every measurement we can make, every signal we can detect, every photon and gravitational wave we can record, all of it comes from outside the horizon. The inside sends us nothing. It's the universe's most secure vault, locked not by any mechanism we could pick, but by the geometry of space-time itself. And maybe that's the most fitting way to think about where we stand. The visible achievements are extraordinary. We have photographed black holes, we have heard them collide. We have built theoretical frameworks of breathtaking mathematical elegance that connect gravity, quantum mechanics, thermodynamics, and information theory into a single interlocking structure. But the hidden core, the deepest layer of reality, the thing that space-time itself might emerge from, remains out of reach.
We can see the shadow. We can hear the echo. But the thing that casts the shadow, the full story of what's really happening in there, that story is still being written. And honestly, that's what makes this field so alive. The biggest questions are open. The tools are getting better. The theory is getting sharper. And the universe keeps turning out to be stranger and more beautiful than anyone expected. Let me pull back for a moment and think about the shape of the story we've been walking through tonight. It started in 1783 with a man in Yorkshire, a clergyman with a gift for Newtonian physics, imagining a star so massive that light couldn't escape. A dark star, an invisible object, detectable only by its gravitational pull on things around it. Michell followed a visible clue, escape velocity, into hidden territory, and arrived at a conclusion so far ahead of its time that the world simply set it aside and forgot about it.
Then Einstein rewrote the rules of gravity, and within weeks, a dying soldier on the Eastern Front found a solution that contained, buried in its mathematics, the shadow of Michell's dark star. Only now, it was something far more radical. A region of space-time where the roles of space and time swap, where the interior is forever disconnected from the exterior, where a singularity lurks at the center and the equations of physics shatter. The solution was visible, published, available. Its implications were hidden, avoided, resisted for decades. Then, a 19-year-old on a steamship worked out that massive stars have no stable retirement. And the most powerful astrophysicist in the world publicly destroyed him for it. The mathematics was visible. The truth was hidden behind the authority of a great man's reputation. Then Oppenheimer proved that collapse is inevitable, published his proof on the day the world went to war, and walked away. The proof was visible. The attention of the world was elsewhere. Then a golden age. Penrose's singularity theorems, Kerr's rotating solution, Wheeler's name. The mathematics became visible. The objects remained hidden. Then Bekenstein and Hawking dragged black holes into the quantum world and discovered that the blackest objects in the universe glow, that they have temperature and entropy, that they eventually evaporate, and that their evaporation creates the deepest puzzle in physics. The question of whether information can be destroyed. The puzzle is visible. The answer is still hidden. Then the observers caught up. X-ray telescopes found Cygnus X1. Genzel and Ghez spent decades tracking stars around Sagittarius A star. The EHT turned the entire Earth into a camera and photographed what everyone said couldn't be photographed. LIGO listened for space-time vibrations and heard two black holes merge over 1 billion light-years away. The evidence is visible, overwhelming, convergent. The interior remains hidden, sealed behind the event horizon. And now, the theorists are beginning to suspect that what's hidden isn't just the inside of a black hole. What's hidden is the true nature of space-time itself.
that space and time as we experience them might be emergent, arising from quantum entanglement, from information, from a deeper layer of reality that we are only beginning to glimpse. The stage on which we thought everything happens might itself be a kind of projection, a macroscopic appearance arising from microscopic quantum correlations that have nothing to do with space or time as we understand them. And that brings us back to the three questions we started with tonight. How did we figure out that black holes must exist? By following visible clues into hidden territory. Michell followed escape velocity. Schwarzschild followed Einstein's equations. Chandrasekhar followed quantum mechanics into the heart of a dying star.
Oppenheimer followed the logic of collapse. Penrose followed the topology of trapped surfaces. Hawking followed quantum field theory into curved space-time. Every one of them saw something visible, something the mathematics or the observations were telling them, and had the courage to follow it into territory that most of their colleagues found uncomfortable or absurd. What do we actually know, and what remains unknown? We know that black holes exist, that they form from collapsing stars, that they sit at the centers of galaxies, that they collide and merge, that they warp space-time in exactly the way general relativity predicts. This is visible, confirmed, tested. We don't know what happens at the singularity. We don't know how information escapes during evaporation. We don't know the precise mechanism by which quantum gravity resolves the classical infinities. We don't know whether the holographic principle works in our universe as cleanly as it works in anti-de Sitter space. All of that is hidden. And what does the darkness teach us? Maybe the most profound lesson is this. The universe's deepest truths may not be visible in the way we expect. They may not be things you can see or touch or photograph. They may be structural, mathematical, informational, woven into the pattern of correlations and entanglement that underlies everything we experience. The darkness of a black hole isn't an absence of information. It's an invitation to look for information in a different way, in a deeper place, at a more fundamental level than the three-dimensional space we move through every day. Every chapter of this story follows the same pattern. A visible clue leads to a hidden truth. Someone has the courage to follow the clue. The hidden truth turns out to be stranger than anyone expected, and the strangeness leads to the next question, which leads to the next hidden truth, which is stranger still. Layer after layer, each one deeper than the last.
Each one more unsettling. Each one more beautiful. And we're not at the end. We're not even close to the end. The singularity is still a question mark. The information paradox is still unresolved. The holographic principle hasn't been extended to our universe. Quantum gravity is still a construction site, not a finished building. The interior of a black hole is the hardest place in the universe to get information from, and we haven't gotten any yet. The tools are getting better, Lisa. The next generation EHT, Cosmic Explorer, the Einstein telescope. But the deepest questions remain open. And honestly, looking at the history, at the pattern of how every generation's answer has led to a deeper question, I suspect that when those questions are eventually answered, the answers will lead to questions we can't even formulate yet. That's how it works. That's how it's always worked. And you know what's quietly wonderful about all of this? Right now, tonight? Black holes are everywhere.
Stellar mass black holes scattered through our galaxy. The quiet remnants of massive stars that burned out millions or billions of years ago. Sagittarius A star, sitting at the center of the Milky Way. 4 million solar masses, relatively calm at the moment, occasionally pulling in a wisp of gas. Supermassive black holes at the centers of nearly every galaxy you could point a telescope at. Some actively feeding and blazing with the luminosity of quasars. others sitting quietly in the dark. And right now, at this moment, gravitational waves are rippling through this room, through the walls, through the air, through you. Ripples in the fabric of space-time caused by black holes colliding billions of years ago. Ripples that have been traveling at the speed of light across the universe ever since, stretching and squeezing space by amounts so small that only the most extraordinary instruments ever built can feel them.
The universe is humming with the echoes of black hole mergers, and that hum is passing through you right now, as you lie here. There's something peaceful about that, I think. All of this, the collapsing stars, the bending light, the radiating entropy, the information paradox, the ripples in space-time, it's all happening, quietly, constantly, everywhere. The visible universe is doing what it has always done, and the hidden parts, the interiors of black holes, the true nature of the singularity, the deep structure of space-time itself, those hidden parts are patient. They're not going anywhere. They'll wait for us to catch up. You don't have to solve any of it tonight. You don't need to hold on to the numbers, the names, the dates. They'll be there tomorrow if you want them. What matters tonight is just the shape of the story, the way each generation followed a visible clue into hidden territory.
The way the universe kept turning out to be stranger and more beautiful than anyone expected. The way the questions keep getting deeper, and the tools keep getting better, and the answers keep leading to more questions. And somewhere right now, someone is lying awake, turning one of these questions over in their mind. Maybe staring at an equation. Maybe looking at a data point that doesn't quite fit the prediction. Maybe they're about to notice something nobody has noticed before. And it will change what we think we know. And the story will get richer and deeper and more astonishing. But that's for tomorrow. For now, just let it settle. The dark stars, the warped space-time, the dying soldiers, the steamship notebooks, the colliding monsters, the ringing of space-time, the glowing horizons, the missing information, the hidden fabric beneath it all. Let it all drift into the background, like the quiet hum of gravitational waves passing through the room. The black holes are patient.
They've been here for billions of years. They'll be here tomorrow. And the story isn't over. Not even close. But you can rest now. The universe doesn't need you to watch it work. It never has. It just keeps going. Visible and hidden. Dark and bright. All at once. Everywhere. Always. And somewhere, deep in the center of our galaxy, 4 million solar masses of nothing visible are sitting quietly in the dark, warping the space-time around them, bending the paths of nearby stars, waiting for the next wisp of gas to drift too close. And further out, in galaxies you'll never see with your bare eyes, supermassive black holes sit at the centers of 100 billion cosmic cities, some quietly retired, their accretion disks cooled and faded, others blazing as quasars, outshining everything around them by a factor of 1,000.
And scattered through the spiral arms of our own Milky Way, stellar mass black holes drift in the dark, the collapsed cores of stars that burned out long ago, invisible except for the rare moment when a companion star wanders too close and feeds them a stream of gas that lights up in X-rays. All of that is happening right now, all of it invisible, all of it patient, all of it waiting. The universe has been running these experiments for 14 billion years. It doesn't notice whether anyone is paying attention, but it's nice that someone is. And it's nice that tonight, for a little while, you were part of the story. So let that be enough. Let the questions fade. Let the equations dissolve. Let the dark stars and the warped geometry and the tangled quantum information all drift into the background. the way the hum of a distant machine becomes part of the silence after you stop listening for it.
The black holes will be there in the morning, patient and strange and waiting, the way they always have been, the way they always will be. And the story isn't over, not even close. But that's for tomorrow. For now, just rest. The gravity that's pressing you gently into your bed is the same force that bends light around a star. The same force that crushes matter past every barrier. The same force that carves shadows into the fabric of space-time itself. The quietest force in the universe and the most relentless. It's holding you right now, the way it holds everything. And you don't have to do a thing about it. Just breathe and let it hold you, and sleep.